Good morning, y'all. Morning. You guys you guys are like, but it's a minute early, Dr. H. Give me another minute. No. We're not really getting started. Kind of getting started. Morning, morning, morning. Hopefully get a few more. It's always too early. Uh, it's always too early. Yeah, I figured you were still in AZ. So, but I mean, it's only what, an hour difference right now with AZ? Summer, they're the same as Colorado. Oh, are they two right now? Oh, that's right. It goes the opposite way, doesn't it? Two, three, same as Colorado. Oh man, I can't keep track anymore. Yeah, two. Oh, summer. That's why. Because now it's on West Coast time, basically. Okay, cool. First set of exams are done. Everybody submitted both their lecture exam and lab practicals. So awesome, awesome, awesome. I will get to grading them as soon as possible. You're welcome. Um, Exams should be tough. Exams should examinate your guys' critical thinking skills and your ability to think through problems and find keywords and stuff. But here's what you'll find with my class is if you have studied your butt off, and even if you don't do great on exams, you will still do well in the class because of the way that I designed the rest of the class, right? Your homework is done as a group assignment, your labs are done as a group assignment. There's a lot of, in essence, free points, study guides, tons of extra credit. So the idea is that physiology is hard. We all know that. This is not a novel thing for you guys to know about, and you should be aware of its difficulty. It shouldn't be a surprise, and you should feel that if you know 75% of physiology, that's hella good. And if you know 85% of physiology, then dang, props to you. And if you can get greater than a 95, then you might as well be teaching my class. So, yeah, that's kind of how it goes, and everything else balances out. I promise. I promise. I promise. It's my style. I'm not here to punish you guys. I'm here to teach you guys. And sometimes sometimes learning can feel like a punishment because it's tough. But yeah, just wait. we're we're building the body, and this is definitely not anything that's easy. Definitely not anything that's easy. Within the week, Tariq, I'll get them done as soon as I possibly can. My father and little mama are down from Michigan. They've been down all weekend, but you know, I'm not going to sit down in front of my computer for multiple hours to get them graded until they leave. But they leave tomorrow, so I'll be able to really start grading them tomorrow night. And yeah, you'll get them back within the week for sure. Roof is mostly fixed. Thanks for asking. Yeah, they left a few things undone, and I don't know. It is what it is. I'm making my complaints and getting it all taken care of. Good, Heather. Yeah, my teaching style is very different than many others. I know. Absolutely, Melissa. Yeah, anytime, anytime. I want you guys to learn. So yeah, you will get your you get your exams back. You're gonna get your grades back. They'll be released to you. You know the questions and answers will. That's why that email I sent out is so brutally, heartbreakingly honest. Like, don't cheat and don't cheat me. I work my butt off to make these questions work for y'all and to teach you the material that's in the tests, so that if you guys start to release my test questions to other students, man, you worked your butt off. Why are you making it easy for everybody else? Anyways, whatever. Yeah, I mean, thank you, Andy. That's literally the way I have it designed. Is like the way I teach and what I give you guys to study, it should help you with my critical thinking questions on the exams. That's the point. But let's continue on our route through the human body, because we got a lot to do. We got a lot to do, and I'm glad you guys realized or saw the difficulty in it. But hopefully, it wasn't crazy. Like, I've never seen this before. I never want you guys to feel like you've never seen it before. Like, there's keywords in there that will help you answer the question. Sometimes it takes an educated guess. I love that terminology. Sometimes it takes an educated guess, but the keywords are there and they were taught. That's my plan. All right, so we're going to move out of our transport/communication system. So if you'll recall, you ended A&P1 with neuro. And neuro is all about communication, whether it's sensory communication or your body making some sort of integrated response to send a signal back out to the rest of the body for further communication. Communication is pretty darn key to the human body. Endocrinology, about communication, right? We got ourselves some hormones that get dumped into the bloodstream. They get transported to where they go, where they need to go, target cells, receptors, depending on whether they're polar or non-polar. The transport function is different, and the cellular response will be different. And we're going to be seeing a lot of these hormones through the rest of the semester. So don't lose sight of that chemistry. Don't lose sight of it. You don't lose it. Okay, you're going to use it. Technically, you shouldn't lose it. Now, we're going to start to move into the quote-unquote major organ systems of the body, the ones that people really start to look at it for differentials in terms of, if you guys don't know, differentials are like diagnostic tools. When you're looking at a patient and you're looking at what's wrong with them, those are called differentials. So we're going to start really looking at these different organ systems that are used for differentials. So heart, digestive system, respiratory system, and urinary system. And we're going to start off with heart. I don't even remember what my easy question was on the lab, but you're welcome. Lab isn't supposed to be tough. Lab is supposed to be, did you do the work? Here, spew back the info to me. You don't have to critically think for a lab. You will have to for a lecture, but not for lab. So, heart it is. What's the function of the heart? What's the function of the heart? Let's get a few more people to write down the function of the heart. I want to see if anybody has a different answer. Keep you alive. True. Transport. Yeah, because it definitely, since blood is such an important part of transportation, man, if we're not moving blood through the body, transportation just doesn't occur. So great answer. Love it. I love it, love it, love it. Anybody else? What's the function of the heart? Or a function of the heart? Doesn't have to be the major function of the heart. Close your eyes. Think about your heart. I'm not looking for a specific answer here. I'm just trying to see what you guys are thinking. Oh, good. O2, CO2, of course, because of the whole transport function. For sure. Oxygen and carbon dioxide, extremely nonpolar. Extremely, both. So they do not dissolve in water. Not very much. Homeostasis, regulation of what? Homeostasis, regulation, same thing, stability, internal stability of what? What sort of things might they be involved in? Heme groups, globin groups, a lot of that's related to blood and the transportation of O2, CO2, Tariq. So good. I love that you're you're focusing on this idea of moving O2, CO2. Obviously, the blood transports a lot more than that, including water. But homeostasis, regulation of what? Now I'm starting to get down to a specific answer. Pace, organs, sure. All right, let me just get you guys to think about this. Oh, there we go. Alyssa, perfect. That's exactly what I was looking for. The very last thing that she wrote, BP. What does BP stand for? If anybody wants to guess a gander. Blood pressure. It's not the only regulator of blood pressure in the human body, but gosh, your heart's not working, no blood flow, no blood pressure. Does that make sense? We'll get into this. We'll talk about this cardiophysiology and how it interacts with the vasculature. But yeah, okay. Now, let's get back on track here with cardiophysiology and basically the number one function of the heart. The number one function of the heart is to pump blood. And when it pumps blood, it's going to be doing all these other things as a byproduct of pumping blood. But what do you guys think in medicine? Do we care about that single heartbeat? Or do we care about what's happening to that patient over time? Over time. A single heartbeat in and of itself isn't really all that important. It's really not that important because you can get one outlier. Well, you can't judge a disease based on one heartbeat. You just can't. It just don't work. So you have to look at what's happening to that heart over time. And we normally look at how the human body works over a 60-second period of time, and then we start to make some judgment calls based on that. Okay, so cardiophysiology. If we start looking at the function of the heart, and we want to simplify the heck out of it, we say that it pumps blood, perfect, over time. Okay, does that make sense? In other words, another way to think about this is when we're pumping blood, what we have are chambers. We have these big ventricles that when they contract, pressure is going to build up inside of these. They're like water balloons. And if you squeeze on these water balloons, as the pressure builds up inside here, doors are going to open. Those valves are going to open and blood is going to get ejected. Literally the term used, ejected out into the system, just blowing out like a volcano, like a geyser. The amount of blood that's ejected, well, blood is a liquid, so we're looking at a volume. So when we say pumps blood over time, what we're really thinking about is a specific volume of blood being ejected by the heart over time. Does that make sense? We're looking at a volume. It's not just pumping blood, it's actually pumping a specific volume. So when we talk about cardiophysiology, we're asking ourselves, what is the volume? Typically in milliliters of blood ejected, that's literally the word, you out of here, ejected from the ball game, ejected from your heart. Over time. And when we're talking about time in the body, we normally talk about 60 seconds or 1 minute. So we're going to say minute. So what is the volume of blood ejected from the heart over time? Well, now when we start to look at units, units are really important to me. Whether or not you learn them well enough in A&P1, I don't know. But all that dimensional analysis stuff that you guys were supposed to learn is related to units. A number without a unit don't mean shit. That's how I feel about it. Numbers, by in and of themselves, have no meaning. What does 6 mean? It means nothing. But if you say there's 6 liters of blood over a minute period of time, now we're starting to get somewhere. That's volume's way too high, by the way. Nobody moves 6 liters of blood in a minute. But I'm just trying to give you guys an indication that numbers in and of themselves mean nothing. How many miles did you drive? 7. 7 what? 7 miles. Now we got something that means something. You guys get what I'm saying? A number without a unit. How old are you? 40. Well, what does that mean? 40 years old. You guys following what I'm throwing down? These are called units. And if you don't have units, say for instance in your lab practicals and your lab reports, I will mark it wrong because a number without a unit means nothing. We're looking at a volume of blood ejected from the heart over time. So we're talking about total units of mils per minute. That's the function of the heart, is to pump blood in mils over time per minute. Mils per minute. Don't worry, I got a point. I'm going to tie all this together. This definitely means something. Mils per minute. Well, we can summarize this definition with keywords. And you're never going to forget these keywords because we're going to use them over and over and over and over and over. The volume of blood ejected from the heart over time is called cardiac output. Okay? This is cardiac output. Cardiac output. One of the most important things that your body does. It's constantly monitoring and regulating cardiac output. It has to make sure that the heart is pumping the appropriate volume of blood over time. And we abbreviate this as CO, capital C, capital O. Just learning pieces of the puzzle here. And we're going to tie it all together. I promise, I promise, I promise. Everybody, what is the volume of blood ejected from the heart over time? How can we define that? What words can we use to define the volume of blood ejected from the heart over time? Good. Cardiac output, cardiac output, cardiac output. Great. Awesome. So how do we go about determining cardiac output? If this is the function over time, actually, this is something we can measure. This is something we can measure as medical specialists of the world. Sonographers are going to do the large majority of this measuring, by the way, because they're going to look at echoes of the heart, and they're going to actually measure the physical volume of blood being ejected out of the hearts. Sonography is a tough program. Lots of work expected of them. So what's going on in the heart, and how can we define cardiac output even better? And how can we start to understand how it's regulated? Well, now we get to go back to some of the anatomy of the heart. Okay, the heart is made up of two major types of muscle cells. So when we start thinking about the heart, we're going to start thinking about two major types of muscle cells. And you're going to be thinking about these every single time that you start to study the heart. Okay, they're called cardiomyocytes. So there's two major cardio, heart, right? Myo, muscle, cytes, cells. Cardiomyocytes means heart muscle cells. And there are two major types of cardiomyocytes. One are called autorhythmic. So there's autorhythmic cells. And two, there are what's called myocardial cells. And we're going to go ahead and for this semester, I change it a little bit every semester, but I want to make sure that you guys have a good understanding of what they do. And we can do that by defining their names a little better. These are called contractile myocardial cells. So there are two major types of cardiomyocytes in the heart. The first one's called autorhythmic, and the other one's called myocardial. Autorhythmic, there's not very many of them. Even though I wrote major, they're really darn important. In fact, less than 1% of all of your cardiomyocytes are autorhythmic cells, so not very many. The rest are contractile myocardial cells, so greater than 99% of your heart cells are contractile myocardial cells. Almost lost my marker. Autorhythmic cells, you can abbreviate AR. And then the myocardials, just write out myocardial, okay? So autorhythmic, you can abbreviate capital A, capital R. I'll always understand that if you're writing it in chat. So what are the two major types of cardiomyocytes, y'all? Just a little bit of redundancy. Such an important part of learning cardiophysiology. Okay, Alyssa. Which one of these do you think creates the pressure that's going to cause that heart to eject the blood? Ha! You got it. You got it. You got it. You got it. Awesome. All right. Let me just tell you guys just a quick story. I have a heart condition. I have supraventricular tachycardia. Once upon a time, it was called paroxysmal atrial tachycardia. I was diagnosed with it when I was in 8th grade. I was doing my PE class, and they make you run that mile, and I was in the middle of the mile, and then I woke up in the locker room surrounded by EMTs, and apparently my heart had stopped. So pretty cool. Glad to be alive. And when my next door neighbor was an anesthesiologist, and I was her stable boy, so I would take care of her horses and stuff. So she immediately diagnosed me with this SVT, this PAT, and sent me and referred me to a cardiologist. Pretty cool. Now, one of the things that I remember the most, 8th grade, made a huge impression on me, was that my cardiologist was able to really dumb down cardiophysiology for me, really help me understand it as an 8th grader, because I had to learn about my disease. And one of the things that he explained to me is that your heart was going too fast. That's tachycardia. We'll get more into that later. And when I was trying to understand why and how my heart was going too fast, what he said is that your heart is too leaky. Can you imagine an 8th grader hearing that their heart is too leaky? Like, what does that mean? And so he started to explain to me that cells are leaky, that they have these doors that allow things to leak through them, and that my heart was too leaky. And that's what caused my heart to go too fast. And I thought it was such a great beginning lesson, because the cells in your heart that are leaky, they're going to determine your heart rate, because what's going to happen is ions are going to leak into those cells over time, and they're going to be changing the electrical potential of those cells. As ions move across the cell membrane, electricity changes. True story? You guys kind of all know that, remember that, have some base reference in that. And then something else, one more tie, one more piece of the puzzle. Just follow along. You don't need to write any notes on this. We'll get to there. Another, I always have these little stories in life. So I grew up in Alaska, and I grew up fishing. We used to catch these big, king salmon. We'd go out pretty much every single day to go fishing or crabbing or shrimping or something, because it's sustenance living. You got to catch what you're going to eat. Gallon of milk's $10. You don't just go to the store and buy your food. You got to go and get your food. And I was probably about 4 years old or so, and my dad just looks down at me and says, "You want to see something cool?" And we just caught this king salmon, and I go, "I'm 4, right?" I'm nodding my head. He goes, "Cup your hands." And so I cup my hands like this, and he drops the fish heart into my hands, just the heart. What do you think that heart was doing? Just sitting there, not doing anything, or it was beating? I mean, and it's beating like crazy. And so then my dad takes some of the ocean water, which is super salt water, right? It's this great hypertonic solution, and he drips it into my hands, and what do you guys think that heart did? It beat even stronger. And then he had me put the heart on this plank of wood, and the heart beat up. It actually moved its way up this angled plank of wood. There we go. It beat its way up that angled plank of wood because it was so strong. What is this story trying to tell you? Can the heart beat all by itself? Does it need any input from the rest of the body in order to contract and relax? Yes or no? Can it beat all by itself? Yes or no? It can beat all by itself. Is everybody following me on this? It actually needs zero input from the rest of the body. It will get input from the rest of the body, but it doesn't need it in order to function at a normal, regular rate. And then the rest of the body is going to try to control the heart. The word auto in Latin means self. So like automobile means self-driving car. Auto means self. Self-rhythmic, what is that going to tell you guys? That this keeps its own rhythm. Yes, no, maybe so? What is the rhythm that it's producing? It's producing electricity. So autorhythmic cells are able to produce their own electrical signals, action potentials. And they do not need, let me repeat that because students get this wrong every semester, they do not need input from the brain to create those electrical signals. The heart itself can produce its own action potentials. And it's the autorhythmic cells that do this function. So autorhythmic cells produce their own action potentials. Capital A, capital P, AP's action potentials. Yeah, like a car battery. Of course, a car battery, we don't need to go into the whole alternator thing, but cars have their own way of recharging the car battery. I guess technically we do too, because we have to consume foods with ions in them, and therefore we recharge our car battery. So we're not a whole heck of a lot different. But thank goodness our car batteries go a lot longer than a car battery does. So these produce their own action potentials. And the way these action potentials are going to, do their function is they are going to be created due to the leakiness of autorhythmic cells. You're going to learn. I'm just teaching you guys a couple key words, and you're going to learn all about the leakiness. Okay, produce their own action potentials, and they do this because why? Because they are leaky to ions. So I'm going to literally write in quotation, leaky to ions. And you guys are going to see which ions they are leaky to and how we can change the leakiness of these autorhythmic cells. But just imagine, what if something, and it's not sodium, but I'm just making you guys think, what if something like sodium were leaking into cells? What would happen to the charge on the inside of that cell? Increase? Does it become more positive or more negative? If I had sodium leaking into my cells, cool. Now, what if I had calcium leaking into my cells? What if I had calcium leaking into my cells? What would happen to the charge on the inside of the cell? Become more positive or more negative? Lovely, lovely. And what if I had potassium leaking out of my cells? What would happen to the inside of the cell? More positive or more negative? You got it. So as we change the leakiness of this membrane, we can actually change the polarization of that membrane. And it's a really beautiful synergy. We're going to draw it all out. Real cool. So autorhythmic cells produce their own action potentials because they're leaky to ions. And the way these action potentials are created is that ions will leak, and then there's going to be that refractory period that you guys learned about in A&P1. There's going to be a period of time where another action potential cannot be created, and then the next action potential will be produced. And this occurs about once every second. On average, an action potential will be spontaneously created about every second. So how many times will that action potential be created every minute? And what does this sound like? What's going on here? Every single time an action potential is created, what do you guys think is going to be happening next? Ah, yes. Does this make sense? Every single time that action potential is created, it's going to end up resulting in a heartbeat. Yes, no, maybe so? We'll come back to this in just a second. Yes, no, maybe so. We got a maybe so. Okay, the answer is definitely so. It's definitely a yes. They produce their own action potentials, and these action potentials are going to go to the next location. So they're going to travel through the heart. And we're going to learn all about the conduction of this electrical signal through the heart. They're going to travel through the heart, and they're going to be making it to all of these cells. In AMP1, when you guys were learning about the contractile neuromuscular junction cells, right? We got skeletal muscles that are extremely contractile. What was required to start that contraction? Aha. Right? We already drew this in our class earlier, so I'm just going to reuse this image. But we had an action potential that makes it down here to the terminal bouton to release a neurotransmitter on the heart. What happened next? Well, we had nicotinic receptors. This is only on skeletal muscles. I'm just trying to prove a point. We had nicotinic receptors, and when the acetylcholine binds to those nicotinic receptors, to acetylcholine per nicotinic, then sodium rushes into that motor end plate faster than potassium left. So what starts happening to the charge on the inside of that motor end plate? More positive or more negative? And this was called an end plate potential. And what happened when this end plate potential reaches the sarcolemma? We created a new action potential. You may or may not remember that point. It just depends on how strict your professors were. But when that EPP, when that end plate potential reached the sarcolemma, we create a new action potential. And then that's that action potential that traveled, well, across the T-tubule, but also down into the T-tubule and started activating those DHP and the ryanodine receptors and stuff. True story? Sorry, my lightning bolts suck. I've never figured out how to draw them. But this creation of a new action potential, well, that's where we're at with the autorhythmic cells. We can bypass all of this because autorhythmic cells create their own action potential. So we literally get to start at this point in the puzzle. Does that make sense? If we have cells that can produce their own action potential, then we don't need a neuromuscular junction for our function. Pretty cool. Pretty cool. So these action potentials created by the autorhythmic cells are going to now conduct through the heart, and they activate these contractile myocardial cells. These are the muscle cells, just like skeletal muscle, but these are cardio. These are specific heart cells. And when these contractile myocardial cells receive this action potential, it's going to cause these cells to have their own action potential. So they're going to have, or whatever, produce an action potential. So they're going to create their own action potential once we're following, once they are activated, A with an arrow up, that's what I always use for activation. Once they are activated by autorhythmic. action potentials. So these autorhythmic action potentials travel through the heart, and they are going to come into contact with the sarcolemma of the contractile myocardial cells, and that's going to cause the contractile myocardial cells to create their own action potential. And once they've created their own action potential, now they can contract. Is everybody with me? We're going to go through the contraction process. It's a little bit different than skeletal muscles. What else is essential in looking at cardiac output over time? So they wouldn't be able to create action potential without autorhythmic. Well, that's not true, Jen, but I'll explain why. You're not wrong and you're not right at the same time. And I know you're asking this question, but let me get back to that, okay? It's a cool question. It's a really cool question. It's what we can do to manipulate the heart in a medical situation. But where was I? What was I saying? I forgot. Oh, what else is critical? We just had a heart contraction and blood was just ejected from the heart. What must happen next? So important. So important. Did everybody follow what Andy wrote? We can't just have heart contraction. We can't, if heart contracts and doesn't relax, we'd be dead. If the heart contracts and only slightly relaxes, it's not going to fill back up with blood. And then the next time it contracts, not enough blood's going to be ejected out. We're going to start having issues. Does that make sense? So the heart doesn't only need to contract, but when the action potential goes away, the next stage is going to be relaxation. And many cardiophysiologists, me, are firm believers that relaxation of the heart is just as, if not more important than contraction of the heart. In fact, most heart failures come because the heart isn't relaxing properly. Over 60% of all cardiomyopathies are caused because of the improper relaxation of the heart, not because of the improper contraction of the heart. Kind of crazy to think about, huh? It's called diastolic heart failure. So let me get you guys to look at this. Every single time that heart contracts, yep, you got activation, activate, just depends on the sentence. You produce an action potential once they are activated. You just kind of, go with the sentence. You guys are all writers. So yeah, A with an arrow up, E with an arrow up, excitation, I with an arrow down, inhibition. So just shorthand so you guys aren't writing massive amounts of notes and words all the time. But let's think about the contraction of the heart and how it relates to its function. If the heart contracts, what did I say is going to happen to the pressure inside of those chambers? Increase, decrease, no change. And as the pressure increases inside those chambers, assuming those chambers filled with blood, it's going to end up ejecting the blood from the heart. True story? And you're going to get a specific volume of blood that's been ejected. True story? Does that make sense? Depending on how strong it contracts. If it contracts stronger, what's going to happen to the volume of blood that gets ejected? Increase, decrease, no change. Cool. So we have just solved the mystery. What is the volume of blood ejected from the heart? That is this portion of cardiac output. It's determining the volume of blood. Yeah? That's this right here. That's that volume. And the contraction of the heart, and by the way, the relaxation of the heart, is going to determine the volume of blood that can be ejected out. Contraction and relaxation determines ejection volume. Does everybody follow my logic on that? Sweet. Now this is just a single contraction relaxation. So we're not looking at anything over time here. We're just saying the heart just contracted and relaxed. Just contracted and relaxed. But what's going to allow the heart to contract and relax over time? Yes and no, Heather. It just depends on the heart. We'll come back to that. Yeah, lifestyle, exercise, cardiomyopathies, you know. Yeah. So what's going to allow that heart rate? Sorry, I just gave away part of the answer. What's going to happen? What's going to allow this heart to contract and relax over time? What's determining how many times it contracts over a period of time? What's specific? And Ashley, you're on. I'm just trying to get other people to see it as well. Sabrina, you're not wrong. The heart rate, the heartbeat, right? You guys with me on that? What cells, though, what cells are going to be controlling your heartbeat and your heart rate? What cells are going to determine how many action potentials are created over a period of time? Oh. So this is going to determine the ejection volume, but when they produce their own action potentials, this determines time, right? This determines how many heartbeats over a period of time. It's called your heart rate. This determines your heart rate. So this is now related to the time factor up here. Does that make sense? We already found how much volume is ejected. Well, that has to do with those contractile myocardial cells. But which one of these is going to determine the time? That's going to be your autorhythmic cell. Is everybody with me on the differences between the two? I need any feedback on this because this is going to be a huge part of your semester. This is not just heart. This is kidney function. This is respiratory function. This is blood pressure function. It all comes back to how these organs work together. So you got to understand this. All right. So there's a way we can look at this. This determines your heart rate, and heart rate is abbreviated as HR, and your heart rate is determining your beats, there's your unit, per minute. So that's your heart rate. SVT2, yeah. That's real cool. So this autorhythmic cell here is going to determine your heart rate, which is beats per minute. The ejection volume is actually not EV, although I always wished it would be. Physiologists ends up calling this the stroke volume, not ejection volume. So determines the ejection volume is better known as stroke in terms of just the volume. Ejection is still what we call blood being ejected by the heart, but each stroke of the heart, a specific volume will be ejected. So we end up calling this stroke volume, or SV. Does that make sense in terms of the terminology? Stroke volume is a single heartbeat, and it's saying how much blood gets ejected in that single heartbeat. So we're going to call this mils per beat. Stroke volume is mils per beat. How much blood is ejected in a single heartbeat? Well, that's your stroke volume. And if the heart beats stronger, more blood gets ejected from that single heartbeat, and stroke volume is going to go up. Yeah, sprinting. Just get up. If you're sitting at a desk right now, stand up. Because if you're in the sitting position, the amount of blood being ejected from your heart, well, it doesn't need to be that high because you're chilling. Kind of chilling, studying, stressed. But when you stand up, you need a greater blood pressure just to get that blood up to your brain. Otherwise, you might get lightheaded. And so what is your heart going to do in order to get that blood up to your brain? Going to go a little bit faster and beat a little bit harder, and then more blood gets ejected from that heart. So cardiac output is going to be these two things. Cardiac output equals heart rate, which is in beats per minute. Some of you guys have heard this as BPM for my class. Let's try to avoid writing BPM because BPM means beats over minutes, which mathematically you guys are going to see is important. So cardiac output equals heart rate. Well, that determines time. So now we're going to take and multiply heart rate by stroke volume, and that's going to give us our volume. So it's heart rate times stroke volume. True story? And stroke volume is in mils per beat. And what do we know about units? We multiply across, and then we divide out common denominators, common units. So which one of these can we cross cancel? For those that remember their dimensional analysis. Most of you, some of you don't, and that's okay, because I'm going to go back through some dimensional analysis with y'all, but we'll save that for lab. So for now, there's a beats on top, there's a numerator beats, and there's a beats on the bottom, which is a denominator beats, right? Anything over anything. 100 over 100. What does that equal, everybody? You had 100 over 100. What would that be equal to? 1. What if it was A over A? What would that be equal to? So now if I have beats over beats, what is that equal to? Always 1. Does that make sense? It's all the same. Whatever the units are, whatever the numbers are, that's always the same. It's a pretty cool thing. So beats over beats equals 1, and we don't need to write 1 into our equation. So now we're left with cardiac output equals mils per minute. Mils is on top, bottom's minute, and isn't that what we already said at the very beginning of all this? Is that cardiac output equals mils per minute, and we just proved it. Cool beans? All right, so let's do this. This is a formula that you must know for the rest of the semester. Cardiac output equals heart rate times stroke volume. Let's write this big, bold, orange, like a sun flaring in your brain. Cardiac output equals heart rate times stroke volume. Everybody, what does cardiac output equal? As fast as you can in chat. Heart rate times stroke volume, heart rate times stroke volume, heart rate times stroke volume, heart rate times stroke volume. And what did you just, goodness gracious. Sorry, I just had a weird little coughing attack here. Probably dying. It's okay. I'll be okay. Okay, sarcasm. So in case you guys don't know equations, who here looks at an equation, immediately thinks of math, and immediately does this? F this noise. I didn't come here for math. I hate my life. Who here hates math? Go ahead, be honest. It's okay. Sometimes, yes. Normally it's like, 80% of the class that hates math. I mean, if 80% of the class here loves math, great. Can we actually find beats per minute, mils per beats, and calculate the actual cardiac output? Of course we can. And we'll do that in lab. Are we ever going to do that in lecture? I love that, Tariq. Are we going to ever do the math in lecture? The answer is no. Because I am not trying to teach you guys the math in lecture. I'm trying to teach you guys the function in lecture. We learn about the anatomy of autorhythmic cells, the anatomy of myocardial cells, and we are going to determine how that anatomy determines the function and how that relates to cardiac output. So let me ask you guys, and I've already done this, but not with the equations sitting up on the screen. Let me ask you guys, if your heart's beating faster, what's going to happen to the amount of blood being ejected from the heart over time, assuming stroke volume stays the same? So I'll put this in as an arrow so you guys can see this. The question I just asked is, what would happen to cardiac output if that heart is beating faster and we assume stroke volume does not change? What's going to happen to that cardiac output? It's going to increase. And this is what equations are amazing for. They are amazing for understanding physiology, because what's on the left is determined by what's on the right. So if heart rate goes up, cardiac output would also go up, assuming stroke volume doesn't change. What about if stroke volume increases? What would happen to that patient's cardiac output if the heart rate remains the same, but each beat is stronger? What's going to happen to that patient's cardiac output? Increase, decrease, no change. Does that make sense to everybody? Two separate variables, each one with an equal strength on the actual cardiac output. Now, SVT. Here's what happens in SVT, most forms of tachycardia, is the heart rate's going to go blowing through the roof. Mine gets up to about 280 beats per minute. Now, unfortunately, when the heart starts to beat that fast, it cannot relax fast enough. It's impossible for the heart to relax fast enough once it starts going over about 180 beats per minute. It can't relax properly. So if it can't relax properly, what's going to start happening to the amount of blood filling up that heart? Increase, decrease, no change. If it can't relax fast enough, perfect. Less blood can get back into that heart as it's relaxing. So what's going to happen to the amount of blood that can be ejected from that heart when it does contract, if there's less blood in there? So what starts to happen is, even though the heart rate is through the roof, the stroke volume starts to drop. And what's going to happen to that patient's cardiac output? Increase, decrease, no change. It's going a million miles per hour, but there's less blood being ejected. So the cardiac output in that patient drops, less blood to their brain, and they pass right out, because the brain is so dependent on your blood pressure, on blood flow from your heart. Does that make sense in terms of a patient with tachycardia? One of the reasons we worry about tachycardia. All right. I love these equations. Let's keep going with this. Let's keep going with this. This is powerful, super powerful. So let's write this equation down again. What does cardiac output equal, everybody? So now let me get you guys to think about homeostasis. Let's look at a patient whose stroke volume starts to drop. Just the stroke volume. Okay, this is going to be a heart failure patient. Okay, and it just starts to drop initially. We'll see what happens over time. But what's going to happen to that patient's cardiac output? Increase, decrease, no change. But now we got to think about homeostasis. We're going to learn how it relates to blood pressure later, but Does the body like this? Does it like a cardiac output that's too low? No, no, no. Hell no. So what's it going to try to do to stroke volume? Increase, decrease, no change. Yeah, sure, it's going to try to increase it, but this is a patient with a disease, and it can't increase its stroke volume because there's a problem. So what other variable can the body affect? Oh, heart rate. And so as a homeostatic mechanism, what are you going to notice about this patient? When they come through the door and maybe they've walked, up a flight of stairs or whatever, yeah, do you guys see how maybe there'd be a homeostatic effect on that heart rate? And you would be seeing tachycardia in this patient as a result of that drop in cardiac output. The body's like, we can't have this drop in cardiac output. Let's increase the heart rate to try to bring that cardiac output back to where it originally was. I don't know why that was the voice of your body, but it was. Deal with it. We need to bring it back. Oh yeah, definitely. BP would be low, cardiac output drops, such a huge part. But I mean, be low to start with, but then what's the body going to try to do? As the patient's BP drops, what's the body going to try to do to BP? Bring it back up again. So now they're going to be hypertensive, they're going to be super thirsty, and we'll go through all of that next week. So we're not into blood pressure just yet. We're just learning about the heart. This is the power of equations. Equations are extremely powerful for understanding physiology. You don't need to know any numbers to be able to do this. We just say if it happens on the right, something's going to be affected on the left. If there's more than one variable, then the body is going to try to homeostatically regulate it. Pretty cool, huh? I think it's cool. I think it's so cool. I'm going to drink some coffee and bring my heart rate up. So what we need to do is we need to start looking at the how of all of this, because that's my job, right? I teach you guys about these key words like this, teach you guys about the basics of cardiophysiology, and that it's all about cardiac output. But that cardiac output can be determined by the two major cells of the heart, the autorhythmic cells and the myocardial cells. The autorhythmic cells determine heart rate, and the contractile myocardial cells determine the stroke volume. And depending on how well those autorhythmic cells are functioning, and depending on how well those contractile myocardial cells are functioning, we can change cardiac output. Awesome. Let's get into these. Oh, one more thing on this page that was an important thing is that autorhythmic cells, when they produce their own action potentials, those action potentials are now going to move through the heart, and they're going to be hitting the myocardial cells. So the electricity from the autorhythmic cells are what activate the contractile myocardial cells. Does that make sense? So what happens if these action potentials stop? What's going to happen to those contractile myocardial cells? Will they still contract? Yes or no? Correct. The answer is no. They will not still contract. However, what can you guys do in the medical field? Well, yeah, pacemaker will be the eventual, but we can't get that pacemaker in fast enough, so we defib, right? Clear. And what's happening each time that you shock that patient is you're putting current through the entire body. And as that current hits the myocardial cells, it causes the heart to. Now, what you're trying to do is also restart those autorhythmic cells. For whatever reason, they failed. And if you can get the heart to start to beat again, then often it actually does a reboot of the autorhythmic cells. It's a jump start, exactly. When that car battery dies, to use Tariq's analogy, sometimes you got a jump start, and that's what the defib does. Make sense? The defibrillator. Everybody clear. So why is lightning so bad other than the heat? Why is an electrical shock from the walls so bad other than the heat? Because you're creating a current that's traveling through the body and it's hitting your heart. And if you activate the heart for too long with an electrical current, it's going to contract and not relax because the electricity is just still there. And so it's contracting and never relaxing. We're not getting rid of that electricity, and then it's just going to fail and burn out. Cool, huh? So that kind of goes back, and I can't remember who asked that question earlier, but Andy, was that? Anyways, somebody asked that question earlier, and does that answer your question? And it wasn't you, somebody else. I apologize, I forgot who it was. Jen, that's who it was. Yeah, cool. All right, so let's go and talk about some old stuff. Now, first thing I'm going to do is I'm going to be teaching you guys how to draw the imposter heart. You guys don't know how to do this already, I'm sure. There, you're welcome. There's an imposter. It's not what your heart looks like, but it's what we draw. You guys are way better at drawing an imposter heart than I am. Right? It's basically somebody mooning you, but from a top view down. Yeah, there's a butt right there. I don't know why we draw hearts like this. It's not what your heart looks like, but we could use, I think you might be right. I don't know. It's fine. It is what it is. But this heart, we can actually use this heart to understand cardiophysiology, which is cool. You want to be able to draw something nice and fast. So what we're going to do is we're going to go ahead and add our 4 chambers just real quick. So check it out. I just draw a dashed line down to the apex, and I put in 2 chambers on top, 2 chambers down below, and you can see you just got a right atrium, a left atrium, a right ventricle, and a left ventricle. Pretty fast, pretty easy. Makes studying easier. So let's do it. Make sense? So there's our imposter heart. Definitely not what a heart looks like. No blood vessels coming off of this thing at all. Oh, nice. Perfect, Heather. But what we're going to start to do is we're going to start to add our different cell types. Less than 1% of the heart is made up of these autorhythmic cells. And these autorhythmic cells are found in clusters through the heart. The first cluster of autorhythmic cells producing action potentials is found way up here in the sinus of the right atrium. The sinus is basically just a groove on the superior border of the right atrium, and it's called the sinoatrial, SA. Good try, guys. Good try. SV, S node. We're looking at the SA. Okay, so this guy right here is going to be the SA node. It's a cluster. It's a node of autorhythmic cells. And the SA node is also known as your natural pacemaker. SA node is also known as your natural pacemaker or your pacemaker cell. I'm going to go ahead and write in natural pacemaker. Normally, when people get an artificial pacemaker put in, it's because their SA node has broken. And so the artificial pacemaker is going to try to mimic your SA node's function. What do we know about these autorhythmic cells? Is they are going to create action potentials. True story? So let's draw in this action potential with a red marker. I kind of already used a scarlet one to divide, so let's use a blue, a light blue here. So when an SA node creates an action potential, just like the nervous system, we can't, goodness gracious, what's wrong with me? We can't just have electricity running all willy-nilly wherever the hell it wants, because electricity will dissipate as it runs into proteins and stuff. It gets blocked, right? So what we need is we need a conduction circuit. We need wires, just like the wires in your walls. Does this make sense so far? Just like in the nervous system, we have axons. Here we need wires too. Now the wires are a little bit different because in the heart there are no actual wires. There's no axons. But what there are is a specific subgroup of these autorhythmic / myocardial cells with lots and lots of gap junctions. And if you recall, gap junctions are those proteins that allow for one cell to communicate with the cell right next to it via a tiny little gap between those cells. So whatever's happening in this cell will happen in the cell next to it. Do you guys remember those gap junctions? They're in your heart anatomy lecture, narrated PowerPoint, if you guys go back and watch that. But we got this group of specialized conducting cells that are going to allow the current to move through the heart. Now, follow my blue line, and I want you guys to see how this current moves. I'm going to put in some arrows to kind of give you guys a representation of what direction that current is going. So as these SA nodes create the current, it's going to travel out through the atria, from the right atrium to the left atrium, and this isn't the exact representation of how the conduction unit is, but don't worry too much about it. This is a great way to think about it. So all of this current is moving through the atria. And then it's going to reach another cluster. So it's going to end up aggregating all of that electricity, all those action potentials down into another cluster of autorhythmic cells. This one's right on the border of the right atria and the ventricle. So it's called the atrioventricular node, or the AV node. So this is called the AV node. So now we have an SA node, and we have an AV node. I didn't really do a good job drawing that arrow, but we've got an SA node and we have an AV node, and we have a pathway that allows current to travel between these two nodes. We have an SA node, we have an AV node, and we have a conduction pathway that allows for this action potential to move between these two nodes. Is everybody with me so far? In between, in between the nodes, internodal, and it's a conduction pathway, internodal pathways. So here in blue, what we've drawn in are called internodal pathways. We're just going to write pathway, but there are actually quite a few different pathways, but I just kind of drew it in as a figure 8 because it's easier that way, and this is fine for you guys to learn. So when we're going to write a flow chart, we can say the current starts in the SA node. This is the natural pacemaker. This is going to be where most of those autorhythmic cell function begin, the origin of. And that current, that action potential, is going to travel through what? Not through the AV. We're not down to the AV yet. So from the SA node, where does it have to go next? All of that action potential is going to travel through the internodal pathways. So we're going to draw that into our flow chart. Internodal pathways. And those internodal pathways are found in what anatomical structures of the heart? What are these two big chambers up here? Atria. So internodal pathways are going through both the right and the left atria. Atria is plural, atrium is singular. So these are going to be confined to the atria. And the atria have contractile cardiomyocytes. Remember that autorhythmic cells are less than 1%. So what's the rest of this tissue? What's the rest of the cells that these action potentials are traveling through? Does that make sense? That we got tons of what's called atrial myocardial cells. So as those internodal pathways are carrying the action potentials out through the atria, we're going to go ahead and here as a side note, we want to make sure to think about the fact that current is reaching those myocardial cells. So we're going to end up with contraction of those cells. So the atrial myocardial cells will get activated. Now, where does it go next? It goes down to the, what's the next portion? What's going on? Where's all this current going? Goes to the AV node. And what the AV node's going to do is it's going to take and collect all of this current. And it has something called an AV nodal delay. AV nodal delay. It slows the current down. Right now, it's kind of shooting through the atria in a pretty quick manner. And when all that current makes it to the AV node, the AV node's going to say, whoa, I'm going too fast. Slow down. Slow down. How does the AV node do this? The AV node's going to be receiving a signal from somewhere else in the body that's going to help slow it down. What's a great communication system for slowing everything down, for resting systems? Ah, great. Resting systems. Did you guys get the key word there? Rest? So what's going to happen is the AV node has parasympathetic innervation. So we're going to go ahead and write this in so you guys know. PNS is parasympathetic nervous system. And innervation means that there are nerves, terminal boutons, that communicate with the AV node. And this creates a slowdown system. Okay, it's called parasympathetic tone. And we're going to draw that word in, and I'll show it to you guys again later. Parasympathetic tone. A tone or tonicity tells us it's always active. Like a dude that's walking or a girl that's walking down the beach and they got those muscles that are popping. We call them toned, right? Because it looks like their muscles are always active. Well, physiologically, we call them toned because their muscles are always active. So a parasympathetic tone tells us that the parasympathetic nervous system is always active on the AV node, slowing it down. Cool beans? And we're talking normal physiology right now. We're not talking, if you need to increase your heart rate, for instance, if you're running from Mr. Axeman, what are we going to be doing to the parasympathetic tone as we activate the sympathetic nervous system? What's going to happen to that parasympathetic tone? Increase, decrease, no change. Yeah, we get rid of the parasympathetic tone, and now the heart can speed up. See? Oh, no. Loverly. Now, the next part of this pathway is physiologically a bizarre evolutionary trait. It's not the best way to do systems, but what's going to happen is the AV node is going to collect all of this current and is going to slow it down, and then it's going to send it through a single fiber, a single cluster of fiber that's going to go down into the interventricular septum. Remember, the interventricular septum is that big meaty wall between the right and the left ventricles. You got it. So this one right here is called the bundle of His. Capital H-I-S. This is a person's name, not like hiss like a snake. So don't spell it H-I-S-S. His is a person's name. The bundle of His is a single bundle of conducting fibers that travels from the AV node down to the ventricles. And we're coming back why this is not very advantageous. We'll draw this in though, because from the AV node, where's that current going to go next? It's going to go through the bundle of His. Now what? Well, as it travels through the interventricular septum, it starts to branch. Okay, we're just going to get a couple of branches, and as some of these branches of currents are going to go out into the papillary muscles. Some of them are going to go out into the papillary muscles, and the current's going to be able to get into those papillary muscles, and they're going to contract. But the current continues down through the interventricular septum. We are not in severe, like we're not in a place with a lot of contractile myocardial cells yet. It's going to travel down, and it's branched all the way down to the apex of the heart. These are just called bundle branches. So nice, easy word. These are called bundle branches. The whole function of bundle branches, I guess I should say the primary function of bundle branches is to move the current from the AV node bundle of His, to move the current through the interventricular septum to the apex of the heart. So bundle of His, the next part of this is bundle branches. Bundle branches are found within the interventricular septum. And these are going to move all the way to the apex. So what's going to start to happen now that we're at the apex of the heart? Now we're going to have magic. This is awesome. This is what we need. Once we get all of this current down to the apex of the heart, they're going to enter these specialized fibers, very thin threads of fibers that now shoot out through the rest of the heart. They're going to be going, and they're going to come into contact with all of, well, a lot of the ventricular myocardial cells. So all these ventricular myocardial cells in the right and the left ventricles, these fibers here are going to carry the current out to the ventricular myocardial cells. So they're pretty special. They're called Purkinje, P-U-R-K-I-N-J-E, Purkinje fibers. So at the apex of the heart, we now have the beginning of Purkinje fibers. And these Purkinje fibers are going to allow for the transport of the action potential out to the ventricular myocardial cells. Purkinje fibers, what we're talking about now, action potentials to ventricular myocardial cells, or myocardium also works. Does everybody have this written down so far? Okay, cool. This all together, everything that we've drawn out here, both the picture, diagrammatic, and the flow chart over here on the right, this is just called the conduction pathway of the heart. So we're just going to write conduction pathway. So if on a test or on a lab practical or a lab report, I ask you guys to draw the conduction pathway, this is what I'm asking you guys to draw. Is this clear? This is what I want, and I need you guys to understand it, because eventually we're going to learn EKGs, electrocardiomyograms, right? Like electrocardiograms in essence. And EKG, ECG, same damn thing, is a measurement of electrical current through the heart. Electrical current through the heart is an EKG. So what are we actually going to be partially measuring as we look at the electrical current through the heart? We're going to be looking partially at the conduction pathway, and you're going to line this up with an EKG. So when you look at a patient's EKG in the future, certain changes to that EKG will be a representation of changes in the conduction pathway, and you'll be able to determine what's wrong with your patient. It's really cool. All right. You can tell I think a lot of things are cool. That's cool. That's cool. That's cool. Now, let me get you guys to think about something real quick, because I want to take you back to a point that I mentioned earlier. And I said this bundle of His is both great, but also kind of a pain in the ass. What if somebody has a myocardial infarction? This is a heart attack. And the tissue that dies, that's what an infarct is, not an infart, right? And there's no farts in your heart, but there are infarcts in your heart. What if you had tissue death right here at the bundle of His? Yeah, Mitten did. That's right. Did. What if you had tissue death right at the bundle of His? What's going to happen to the conduction of that current to the ventricles? Increase, decrease, no change. This is called a complete block. So this is a bundle block, and they are very dangerous if your patient ends up getting a bundle block. You have to figure out a way to put in stents, and you get that electrical current around where the current bundle of His is. They are bad. If not treated fast, their patient will die. So they are very bad. And that's the way we can end up looking at the conduction pathway. If there's damage to tissue here, damage to tissue here, we're going to affect certain parts of the pathway. But the only place that person's going to just die ASAP, other than, you know, a heart attack that their heart stops, that's not good either. But once you get that heart started back up again post heart attack, if there's damage to the bundle of His, then we can have lots of problems. Anyways, we'll learn more about that when we go through EKGs. How do you guys feel about this material so far? Cardiophysiology function, all about cardiac output. Cardiac output is determined by two major factors: heart rate and stroke volume. The heart rate is determined by SA node, AV node, and all of the autorhythmic cells. But now, as those autorhythmic cells send the current out through the internodal pathways and through the Purkinje fibers, that current will be hitting the rest of the heart, 99% of the heart, which is made up of contractile myocardial cells. Some of them are atrial and some of them are ventricular. But when the current hits those myocardial cells, they will respond by creating their own action potential and then contracting. And when the current is gone, because the SA node only sends out an intermittent action potential, it's like turning the light switch on and then off, on and then off, on and then off. When you turn that SA node off, those myocardial cells get to relax. Let me start runner. One more question, then I'll let you guys take a break. Just to tie a thought process together. What part of your heart beats first? The atria, the ventricles, or neither? Or they beat at the same time? Based off of this information, what actually beats first? The atria, the ventricles, or do they beat at the same time? The answer to this comes from, where is the current seen first? Where do we see the current first? Do we see the current in the atria first? Remember, the current is traveling through this heart. So do we see the current in the atria first, or do we see the current in the ventricles first, or are they going to be in the atria and the ventricles at the same time? Well, according to the flow chart, this must happen first, then we slow that current down, and finally the current gets out to the ventricles. Yes, no, maybe so? So Melissa, Heather, did that make sense? That the atria actually contracts first. The atria contracts at a separate time than the ventricles. Who would have thunk? But it all has to do with conduction currents. And this is cool because the atria has a tiny little reservoir of blood. And so right before the ventricles contract, and remember the ventricles are going to contract and send blood through the rest of the body, pulmonary circuit over here, systemic circuit over here. Right before the ventricles contract, the atria are going to contract and squeeze the last little bit of blood down into those ventricles. And that's going to be the final volume that can potentially be ejected from the heart. So it's pretty cool. There's not 2 beats, Heather. There's not 2 beats. I mean, kind of. But there's really not 2 beats. The atria contracts, and immediately following the atria, the ventricles contract. And you can look at, and we're going to do this, but we'll look at some animations of the heart beating, and you'll see what I mean. It goes atria, then ventricles. Atria, then ventricles. Atria, then ventricles, all in one beat. It's not like the atria contract, then everything relaxes, then the ventricles contract, then everything relaxes. It's all synchronous. Beautiful harmony of electricity. So let's take a break. We got some lab stuff to get through today too. The lab stuff is directly related. I might have made a mistake on the blood safety, blood anatomy, hematology. I think I made a mistake on the schedule with blood pressure and pulse. So today should be blood pressure and pulse. And I had a box that wasn't merged with the other boxes. So we will fix this. Okay, sweet. While you guys take a good 20-minute break, I'm going to kind of move things around and try to fix this schedule. So please be back. What's 20 minutes from 50 after? So we'll go 23 minutes. Okay. I just got the schedule updated and I posted it on Blackboard. You can see it's called AMP2 schedule RRC. Summer 2021, and then I wrote in updated. So that will be the updated version. And in essence, I just moved some parts around for this particular unit. There was something interesting going on down here for our June 23rd lab. It was still blank, so apparently I'd meant to move everything down when I was going through. Anyways, we won't get into it. I always make at least one mistake. This is now, updated on my end. So the exam, of course, was going to be on July 11th, and it said something like July 18th. So now you guys have that in a written form as well. And today we'll be doing a blood pressure and pulse. And then on Wednesday, we'll do a cardio lab. And then next week, we'll look into EKGs and then blood vessel stuff. The blood vessel stuff will tie back into blood pressure and pulse, so we'll definitely have a lot of links between these different labs through this particular unit. It's a very synchronous unit. I love it for that. Right, one thing leads to the next, leads to the next, leads to the next, and I think it's a lot easier to follow than, say, the endocrine system, because the endocrine system is a mosaic of patterns, so to speak, where there's lots of different hormones doing lots of different things, and each thing is kind of, you got to study separately. Well, here, it's all one thing. Anybody have any questions on the schedule, the way that it is now? I apologize for the mistake before. Definitely my admin assistant's fault. Any questions? Am I here? Are you there? Are we there? Bueller. 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 Cool. Heart physiology. We did a pretty good job getting it introduced today. We're going to do a little bit more of our heart physiology because, well, summer. Oh, your fam's still sleeping. Man, your fam are sleeper inners. Going to go away. Yeah. All right. So, do love me some night swimming. Okay, so here's where we're at. We're back on board with what we were learning today. And I want to show you how this matches up with the actual lecture. Cardiovascular system, heart physiology 1. In essence, so far, all we've covered is a review of cardiophysiology. What is the function of the heart? Eject blood over time. I shouldn't be a robot. I have great service today. So maybe the robot is, no, it's not on your end either. So, yeah, my voice is just a robot. All right, so what I was saying is that you guys already have these lecture, and so far, all we've done is we've covered the first slide. That's the way I teach. So the way it's going to work is I give you lots of introductory material. We talk a lot about keywords, and then we start to dive into these other lecture slides. And here's the conduction pathway, right? SA node. But what's missing? The internodal pathways, they exist. You got to be able to get the current from here through the atria down into the AV node. From the AV node, bundle of His. From the bundle of His, bundle branches. And from the bundle of branches, out through these Purkinje fibers. That sound at least familiar to people now that we've covered that together? Lovely, lovely, lovely. Now, autorhythmic cells, these are the guys that create our heart rate and our heart beat. And there are actually clusters of these autorhythmic cells that can create their own action potential, because that is the definition of an autorhythmic tissue. SA node is the primary. It's the natural pacemaker, the normal pacemaker. And the SA node is actually throwing out about 70 to 80 action potentials every minute. And the SA node does have parasympathetic tone, just like we talked about the AV node having parasympathetic tone. So the SA node, if it did not have parasympathetic tone, would be racing at about 100 beats per minute, which would be considered tachycardia. Yes, that's an average of 70 to 80 beats per minute. You got it. SA node's throwing out about 70 to 80 action potentials every minute. And then the AV node would normally slow that down. But what I want to show you guys is that the SA node is not your only pacemaker cell. So what would happen in a patient whose SA node stopped working? Would they just die? Would their hearts stop beating? The answer is no. And why is that? The answer is because they still have autorhythmic tissue. So the AV node is autorhythmic. So if the SA node stops sending action potentials, the AV node is producing its own action potentials every 40 to 60 beats per minute. Every 40 to 60 beats per minute. That didn't sound about, but you know, every second and a half or so. Second to a second and a half. So what does that tell you? It is dependent upon the SV node, Heather. This is if the SA node stops functioning, the AV node can serve an autorhythmic purpose. It can produce its own action potentials. But keep listening to me here. If the SA node breaks, what is that patient's heart rate going to be? Lower. Lower. It's going to be somewhere between 40 to 60 beats per minute. And what if it is 40 beats per minute? Well, what did we learn about cardiac output? What does cardiac output equal? Heart rate times stroke volume. So if you have a patient whose heart rate drops to about 40 beats per minute, what's going to start to happen to that patient's cardiac output? You're already writing. All right, what's going to happen to the amount of blood that's being ejected from their heart? Increase, decrease, no change. Well, we'll get there in just a minute, Heather. We'll get there in just a minute. So cardiac output decreases overall in this patient. Now, as long as they're in the sitting position, laying down, stuff like that, it's not going to impact them as much because the body doesn't need as much blood when you're resting. But what would happen to that patient whose SA node broke? What would happen to that patient if they tried to stand up? Would they be able to get their heart rate fast enough to be able to meet the cardiac output demand? No. And their heart's going to try to beat stronger, but often in those cases, it just can't beat strong enough, fast enough. So those patients stand up to start to walk and they just fall to the ground. They pass out. Does anybody have a grandparent, an uncle, or somebody they know that had to have an artificial pacemaker put in? Yes or no? Or maybe currently is having heart issues? Yeah, Ariana, do you want to share any of that story? Grandma, grandpa, grand aunt, uncle? What were some of the symptoms that they had? Why did they have to have an artificial pacemaker put in? It's almost always the same story. Tariq, you can share yours too if you'd like. A bypass surgery. Yeah, bypasses can definitely end up affecting how strong the heart beats. It doesn't always mean they have to have an artificial pacemaker put in, but often that's a way to be able to increase that patient's heart rate artificially so that it is producing enough CO. Grandpa, yeah, if you don't know much about it, then I could almost guarantee you part of the story is that Gramps used to try to get up out of his chair and he'd just fall to the ground. And potentially, often they don't realize they have what's called bradycardia until they go to get checked at the doctor's office, and they tell them the doctor the symptoms are that they're feeling really lightheaded and that they just don't seem to be able to get to where they need to go without falling to the ground. and then you kind of know for sure that heart rate's too low. So yeah, anyways, and often that's because of damage to the SA node. Last but not least, even if the AV node goes out, your heart can still create action potentials, but 20 to 40 beats per minute, you better get that fixed. Does that make sense? You're not going to live long if you have 20 to 40 beats per minute. No, it cannot heal itself. Normally, these damages are caused because of, small myocardial infarctions or electrical current blockages, and they're just not the very good. All right, cool. I don't test heavily on this. We just spent a little bit more time than I normally went on, but it's a super cool idea. Okay, let's see how far. I think we'll make it through the next thing here. What we need to think about is how. I love asking how, because how is physiology. And what we're going to start with is the how of autorhythmic cells. What do I mean by that? What's the function of autorhythmic cells, everybody? Look what I wrote here. What are they doing as a function? They create an action potential. And how did I say, just using a really easy terminology, my doctor, my cardiologist in 8th grade, what did he teach me? How are they producing their own action potentials? They're leaky. Great job. Great job. I know I'm showing it on the screen, but I love that you guys are following and making these connections. One second. Okay, so action potentials. We reviewed action potentials just a little bit last week. Kind of did it on that scratch paper where we ended up drawing I was too young to really be scared. I didn't know what the hell was going on. I'll tell you one thing, I was very intrigued. I was definitely intrigued. All right, so here's my action potential graph. Please always label your axes. So this down here is time. Things happen in the body very, very fast typically. So this is going to be time in milliseconds. And then over here on the y-axis, this is related to that membrane potential. And what did you guys learn about potential? What is the definition of potential? Anytime in physics and science we hear the word potential, what are we dealing with? Change in charge, minus 70, not untrue. Yeah, difference in charges. And the difference in a charge is voltage. That's literally what it means. So potential has to do with the potential difference in charges between two sides. And this is all related to voltage. Does that ring a bell to everybody, whether or not you remembered it immediately or after it was said? This is voltage. Now, there's small amounts of voltage in the body. We're talking millivolts here. We're talking millivolts. And just to simplify things, I like to always draw this little diagram of a cell. It doesn't need to be perfect by any means, and we don't even really need to label everything perfectly. The cell is just a nice, or the circle is just a nice representation of all cells in the body. But myocardial cells are not circular. Okay, myocardial cells are not circular. I don't know if you remember this from AMP1 or not, but myocardial cells are actually a little bit more on the columnar side, and they branch, and they got sticky ends, and where those sticky ends come into contact with one another, if they stick to another cell, that's where the intercalated discs are at. So this is actually what a myocardial cell truly looks like, but we just draw it as a circle because it's easier. Is that clear to everybody? If you want to learn more about these, just look at the narrated PowerPoint on the cardio anatomy. It's there. It's online for you guys to look through. So in a normal cell, we have a sodium-potassium ATP pump. Well, all cells of the body have these. So we have sodium, potassium pumps. Sodium, potassium pumps, always moving sodium out and potassium in. Easy way to remember this. What ion has its greatest concentration outside the cell? Sodium. What ion has its greatest concentration inside the cell? Potassium. Lovely. We draw this in here too, exact same idea. All right, a sodium potassium pump, sodium out, potassium in. For regular membrane potentials, we said now that the cell membrane has lots and lots of potassium leak channels. Ah, there's that word leaky again, right? In a normal cell, there's lots of potassium leak channels. Okie dokie? Everybody following so far as a review from last week? And as potassium leaks out, what's happening to the charge on the inside of the cell? Does it become more positive or does it become more negative? Good. And so if everything is equal, we're up here at 0, but everything's not equal because potassium's leaking out of that and out further, and more potassium leaks out. And what did I say the membrane potential would be if there was nothing but potassium leak channels? Anybody remember? What would it become if there was nothing but potassium leak channels? If you remember, good? Yeah. This is important. I don't just mention these things for poops and giggles. Negative 90 millivolts. If there was nothing but, no, Tariq, don't jump the gun, my friend. That wouldn't be hyperpolarization in that particular type of cell. We'll get back to that. Cells can have different numbers of channels. So negative 90 millivolts in a neuron or skeletal muscle, that would be hyperpolarization. But different cells do different things. And in neurons and in skeletal muscle, we know that the resting membrane potential is actually at negative 70. Why is it at negative 70? What else exists in the cell membrane besides potassium leak channels? What else do we have here? What's going to make the inside a little bit more positive? Good. So sodium leaks in, it's going to bring this up just a little bit. Does that make sense? And this is how membrane potentials in most cells of the body are created. But guess what? Cardiomyocytes are not most cells of the body. Cardiomyocytes are unique. Cardiomyocytes have something else that's in their cell membranes. They have a calcium pump. So out here on the plasma membrane, and be here too, right, in this particular picture, these would be covered by calcium pumps. So if I have a calcium pump, where did we learn? Where's calcium higher? Some of you didn't know this last week, but then I tried to reteach you guys. Where's calcium higher? Outside the cell or inside the cell? O or I, out or in? Yeah, it's outside the cell. So what do we know about pumps? Is they're always moving things from high to low or low to high? Using ATP? Are they moving things down a hill or up a hill? Low to high or high to low? Everybody with me so far? They're always moving things low to high. They're pushing a ball back up a hill. You're putting energy into it to make it do its function. So Calcium pumps are moving calcium out of this cell. So what's going to start happening to the calcium concentration outside the cell? Increase, decrease, no change. Yeah, so now we're getting a lot of calcium out here. We get a lot of calcium out here. So what if I were to add one more thing to this system? A calcium leak channel. So what if I put in a calcium leak channel? Since calcium's higher out the outside of the cell, it's getting pumped out, what's going to happen as long as this calcium leak channel is open? Calcium is going to move from high to low, and it's going to go inside this cell. So what's going to happen to the charge on the inside of the cell as calcium leaks in to this cell? Same thing that we've been dealing with up here. We got a calcium with 2+ charges. The inside of the cell is going to become even more positive. They are not balancing each other. You'll see, Heather, we're going to draw some more stuff into this picture. But now calcium's leaking in. So as calcium leaks in, it becomes even more positive. So we don't only have sodium leaking in, but we also have calcium leaking in. So the resting membrane potential in these cells is not -70. We have more positive charges leaking in. So instead, it's about -60. See why I kept on trying to stop you, Tariq? Stop thinking of everything you've learned before, although it's important. But because of the anatomy, we create physiology. And if the anatomy is different, then the physiology is different. Y'all following me? So for an autorhythmic cell, because they are leaky, I'm spelling it totally wrong, I think. No, that's right. Autorhythmic cell action potential, because their membranes are leaky to calcium too, their resting membrane is a little bit higher. And it's over here at -60. So this is their RMP. Function follows form, always. Form changes, function changes. So everybody, what is the resting membrane potential of an autorhythmic cell? And it's -60 millivolts. Don't forget units, for future reference. I love units, they're my friends. Otherwise, -60 doesn't mean much. -60 volts versus -60 millivolts. Huge difference in electrical potential. Awesome, cool, wonderful, beautiful. All right, let's do that for now. Let's do that for now. Now, I'm going to draw a cell membrane, I don't know, somewhere down here. So I got a cell membrane, and we're just going to start throwing some proteins into this structure here. I leave gaps for my proteins to go in. So here's my phospholipid bilayer, and we'll go ahead and put in, I don't know, we'll put in a sodium leak channel first, just because. Put in a potassium leak channel, just because. I'll label these in just a second. And then we'll put in a calcium leak channel, just because. Sodium leak channel. I think I said potassium leak channel. I'm trying to color code them, color match them over here, and then calcium leak channel. You may or may not remember me saying this, but I always write these. So the outside of the cell is on top. Just try to be consistent. So this is ECF over here, and then this is ICF over here. So top is ECF, bottom's ICF. All right, let's assume we start at resting membrane, but does everybody have this ready to go? Everybody have this drawn in? Okay, if anybody needs more time, let me know. Let's assume we start at -60. This is the resting membrane potential of an autorhythmic cell. Again, what makes an autorhythmic cell an autorhythmic cell? It's leaky. Yes, no, maybe so? And it creates its own action potential due to this leakiness. Creates its own action potential due to this leakiness. So what if we had a sodium leak channel that was open? Sorry, I'm kind of going up and down here. If I had a sodium leak channel that was open, sodium's higher outside the cell, therefore sodium would leak into the cell. And would that make this more positive or more negative? I know redundancy, you guys are starting to see this over and over, but it's a great way to learn. So if that were to happen, my curve would go up towards the zero. What if it was a potassium leak channel? What would happen if we had an open potassium leak channel? Potassium's higher inside the cell, so everything's going from high to low, and potassium would leak out. So what would happen to the inside of the cell? Would it become more positive or more negative? And last but not least, we got calcium. If I had a calcium leak channel, well, calcium's higher outside the cell. Therefore, calcium leaks in, and it would become more positive. All right, cool. Now, what if I told you, physiology is so complicated sometimes, but what if I told you that we had leak channels? We had sodium leak channels, we have potassium leak channels, we have calcium leak channels, but then we also have sodium, potassium, and calcium leak channels that are transient. What is this word transient? Transient means temporary. Okay, it's there for a short duration, then it goes away. Transient means temporary. What a transient leak channel is, we call them T-type channels. And T-type channels are transient type. What a T-type calcium channel or a T-type sodium channel or a T-type potassium channel is it's open. It's got actually a trigger that will cause this leak channel to open for a short period of time and then close again. So this transient opens and closes. So it's actually a leak channel. It's not like a gated channel. This is not a chemically gated channel. This is not a voltage gated channel. It's a leak channel that's only open for a short period of time and closes for a short period of time. It's a T-type. Next, these T-type calcium channels and T-type sodium channels and T-type potassium channels, they have specific names because why not? Why not make it even more complex? The first transient channel that I'm going to teach you guys about is called a funny channel. I'm not joking. This is not supposed to be funny. It's literally called a funny channel. And the reason why it's called a funny channel has to do with one physiologist that found this thing. Yeah, found this thing and said, man, this thing acts funny. I've never seen this before. And so he went to a big conference and they were all, saying, hey, there's a funny channel that I've never seen before. And I don't know what the hell's going on with this. And the name stuck.
it's a funny channel. And so now to this day, we call this thing a funny channel. And funny channels are these transient or T-type sodium channels. So what can go through funny channels, y'all? What ion can pass through a funny channel? Sodium. Sodium. Cool. Next, there are T-type calcium channels. And we can just call them T-type calcium channels. That makes our life a lot easier. There's no specific, hilarious channel. That doesn't exist. Slap my knee channel. That doesn't exist. The funny channel is the only weird outlier. Whatever. Yeah, an LOL channel. That's what we should have, right? I know, Tariq, right? And then last but not least, and one we don't worry about as much, but we're going to come back to it. Okay, it's not going to be immediate, but we're definitely going to come back to a T-type potassium leak channel. There are actually going to be T-type potassium voltage channels too you're going to have to learn about. So that's why I wrote in the word leak channel, so you guys can realize there's a transient potassium leak channel out there. Yep. Don't worry, we're breaking it down, pieces of the puzzle, and then we're going to throw it all into the story, and hopefully by creating the pieces and then putting the story together, everything will make a lot more sense. So down here, if I had a sodium leak channel that was closed most of the time, but then opened and then closed, what kind of channel would this be? If it was only open transiently. Yeah, Parker, Andy, you got it? T-type's not what we want to call it because this one specifically allows sodium through it. Although it is a T-type, you're not wrong. But what is the specific name for a transient sodium channel? It's a funny. Versus a calcium one that's only it's gonna be closed most of the time, but opens and then closes. What's that gonna be called? Now, since we're dealing with calcium, it's not funny anymore. Now it's just a T-type calcium channel because these were identified well after the sodium leak channel. So funny was already taken. And then we're going to learn how these ones are regulated later. They're not going to be part of the normal autorhythmic function. Yeah, who knows? So here's what I mean by your heart is normally leaky. Okay, so in order to do that, we're going to start here at resting membrane potential. We're going to start down here. So only the sodium channel is the funny channel. Exactly, Tariq. So we're going to start here at resting membrane potential. So we're going to say the heart is completely at rest right now. Well, what's going to happen first down here at RMP is that a transient channel is going to open for a very short period of time. And when this transient channel opens, sodium is going to pass through it. So what transient channel is open at resting membrane potential based on that logic and sequence that I just did? At resting membrane potential, sodium is going to start to leak into this. So which of the transient channels is open at resting membrane potential? It's the funny channel. Good. So right here at step 1, and I don't have room on this page to do it, so you guys do it. At step 1, the funny channel is open. Please write that down. Step 0, if we were to come down here to 0, step 0 is resting membrane potential. So here at 0, we're at resting membrane potential. So at 1, what happens at the very beginning of 1 is the funny channel opens. And when the funny channel is open, sodium enters the cell, making the cell more positive. And this is going to go to about negative 50 millivolts or so. Negative 50, negative 55, it kind of just depends on the person, but it's not open for very long. Just opens and closes. Well, as it's closing, another one of these transient channels is going to take over. And it's going to be this T-type calcium channel. So at this point, calcium is going to be entering the cell through a T-type calcium channel. Boom. It continues to be positive, doesn't it? Calcium is leaking in. So here at step 2, the funny channel closes. Please write that down. I'm going to be doing this flow chart for you too. But at the very beginning of number 2, the funny channel has to close, because if the funny channel doesn't close, both sodium and calcium enter at the same time, and this line is going to be steeper. Now, that's important. So at the beginning of 2, the funny channel closes, and the T-type calcium channel opens. So what ion will be entering the cell at this point? Here at 1, it's sodium, and here at 2, it's calcium. Positive charges entering that cell, making the inside of the cell more positive. Wonderful, perfect, just fan-diddly-tastic. Now, this color will work. Now, what's going to happen is it's going to go to about negative 40 millivolts, at which time, I'm going to go ahead and draw a dashed line across here, at which time a voltage-gated channel is going to open. At which time a voltage-gated channel is going to open. This is called threshold. It's exactly what the definition of threshold is. Threshold is the energy required to open up a voltage-gated channel. Threshold. If we wanted to define threshold, we would define threshold as the energy or voltage required to open up a voltage-gated channel. It's an important definition. I think students miss this a lot. Does anybody? Yep. Threshold is the energy required or voltage required to open up a voltage-gated channel. So anytime you see the word threshold, what you should be thinking about is a voltage-gated channel. Not a leak channel anymore. Voltage-gated. So at threshold, all thresholds, every threshold that you ever learn about, voltage-gated channels are going to open. Does anybody remember what the threshold was in a neuron or skeletal muscle? Exactly, negative 55 millivolts. But what did you just learn it is in the heart? Negative 40. Negative 40. What do we learn just earlier? What do I keep saying? Structure determines function. And if I have something with a different threshold, doesn't that tell you we have a different structure? Yes, no, maybe so. So in skeletal muscle and neurons, what opened at negative 55 millivolts was a voltage-gated sodium channel. Well, this is something that's opening at negative 40 millivolts. So it's not going to be a voltage-gated sodium channel. Instead, it's going to be a voltage-gated calcium channel. So right here at threshold, the T-type calcium channels allowed calcium to leak in until threshold is reached, at which point a voltage-gated, I'm going to go ahead and write in my 3 here, Right here at 3, at the very beginning, at threshold, a voltage-gated calcium channel is going to open. I don't have that drawn in anywhere down here. Yep, at threshold, at about negative 40 millivolts. What's going to open up here, everybody? You're probably writing it in your notes, but I'd like for you to write it in chat. What opens at the very beginning of 3 here? Not just any voltage-gated channel, Veronica, you're not wrong, but a volt, and so let's try to get our terminology straight so everybody's on the same board here. I'm going to draw it down here on this cardiomyocyte, okay? I'm going to put a pink circle, which is indicative of this, pink 3. This is called a voltage-gated, a VG, calcium channel. The order of the words is important because it tells you what its stimulus is, and then it tells you what can go through it. So what's going to open at 3, y'all? Good, Parker. That's what we're after right there, voltage-gated calcium channel. And where's calcium higher, outside the cell or inside the cell? Outside. So now, because they're voltage-gated, nope, T-type, great question, Melissa. At 3, the T-type calcium channel closes. It's only open for a very short period of time, then it's closed. Great question. Thank you for asking that. So at the very beginning of 3, the T-type calcium channel closes. But boom, we're at threshold. So now a voltage-gated calcium channel opens. And what's so great about voltage-gated gates, lots of them, voltage stimulates them to open, and that's going to allow ions not to leak, but to rush. So now we get a torrent. Now we get a flood of what ion, y'all? What ion is going to start flooding into this cell? Calcium. So what's going to happen to the inside of the cell? Does it become more positive or does it become more negative? Good. And this flooding of current is called an action potential. So this flooding of current is caused because calcium is rushing into this cell rapidly through a gated channel. And it goes up to about +5, +10, a little different than skeletal muscle and neurons. Those go all the way up to +20, +30. But this is good enough. Calcium just has a lot more resistance, so it doesn't go quite as high. But it's still an action potential. Still an action potential. How's this going to get back down? How do we get these to repolarize? What ion is always good, Heather? I love that you did this. Heather got, you know, what do they say? Nail on the head, head of the nail, something. I don't never remember the quote exactly, but man, you gotta close that voltage-gated calcium channel first. Does that make sense to everybody? Because as long as this thing is open, all right, we're gonna be fighting against it. This is important. This will be really important for myocardial tissue, which you'll learn more about their action potentials tomorrow. But yeah, we close this voltage-gated calcium channel first. Close that. Use this pretty blue, I don't know, turquoise, teal, whatever color this thing is. I suck at colors. So right here at the very top, this is going to be 4. Right here at the very top, the voltage-gated calcium channel is going to close. And we're going to need to bring this back down. And what ion is really good? What ion is going to be really good at getting, just looking at the ion, I'm not looking for channels or anything like that. What ion is really good at allowing for repolarization? Same ion you guys learned in AMP1 for neurons and skeletal muscle. Good. The answer is potassium, because remember, when potassium leaves the cell, the inside of the cell becomes relatively more negative. So it's going to move back down. True story? Nice. So don't think the leak channel is involved here. This is not a leak channel because what is going on up here is voltage. So just like in neurons and just like in skeletal muscle, up here, what's going to open fully, you guys are going to learn this process with me, but what's going to open fully is a voltage-gated potassium channel. So this is potassium that's rushing out of the cell because a voltage-gated potassium channel opens. Y'all with me? So what's going to happen is that this is going to drop and the funny channel starts to open. We're not going to worry about it too much, but it ends up causing a little bit of a leveling off. Those voltage-gated potassium channels are going to close, and what's going to just take right back over again? We just went 0, 1, 2, 3, 4. We're back at 0 again, so what's going to happen? You got it. You got it. You got it. Great job, y'all. Does it make sense now? This is autorhythmic. It just keeps doing its thing over and over and over and over. So what's going to happen now that we're at RMP is the funny channels, they just open right back up again. Now what's going to happen? The funny channels are going to close, and what's going to open? So those T-type calcium channels open. We get a little bit of leaking of calcium back into this cell. Sweet. It hits threshold. The T-type calcium channels close. And what's going to open? Lovely. Everybody, what I got Ashley that's written it so far. You guys can write it as VG. So just abbreviate here. So VG calcium, and therefore massive rush of calcium into the cell. At peak, the voltage-gated calcium channel closes, and what's going to open? Voltage-gated potassium channels. So now potassium rushes out of that cell. Made that curve a little bit steeper. These guys should look identical, but I didn't do a very good job at it. But nonetheless, get a little bit of a balance. And what's going to open down here at the bottom when it hits RMP? Funny channels, then T-type calcium channels, then voltage-gated calcium channels, then you guys see it's just the same pattern over and over and over, and it does it automatically. It does it because it's leaky. Thanks, I do my best. More like D+, but I'll take it. I use different colors, and I think that helps me with my horrible drawing. So let's think about it two different ways. Funny channel, T-type calcium channel, voltage-gated calcium channel, voltage-gated potassium channel. Funny channel, T-type calcium channel, voltage-gated calcium channel, gated potassium channel. Sodium, calcium, calcium, potassium. Sodium, calcium, calcium, potassium. Sodium, calcium, calcium, potassium. Over and over and over and over through your entire life's existence. Every single time your heart beats. Sodium, calcium, calcium, potassium. Whew. Approximately 60 beats per minute, 60 minutes in an hour, 24 hours a day for your entire life. Autorhythmic. Yeah, everything affects this. The heart's pretty sensitive. Heart's pretty sensitive. But sodium, a little bit less of an impact on the heart relative to calcium and potassium. Potassium, we'll talk about how potassium affects resting membrane potential, but pretty big deal. We'll come back to that. As a segue into that, anybody know what's used for lethal injection? Like, what chemical do we give to people, human beings? Most of them. For lethal injection, anybody know? No? No, not sodium. We give them potassium chloride. That's literally what kills people. That's what's used. So potassium chloride, KCl, right? And it's the potassium hyperkalemia. That'll stop your heart. You won't make it too long if you have too much potassium in your body. So yeah, it's pretty darn important. But we'll come back to that. It's a pretty cool idea and terrifying at the same time. This area right here, from down here, dot, 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 to right here, dot, 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 dot. Between these two lines, oh no, between these two lines is called a pacemaker. Okay, this is the potential of how pacemakers are created. So this is called a pacemaker potential. Above this point, dot, 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 up, all the way back down to the other side, dot, 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 down, everything between these two lines is an action potential. These are autorhythmic, AR, action potential, AP. So everything between those two dashed lines there are autorhythmic action potentials. Everything down here is pacemaker potential. Up here is autorhythmic action potentials. Yeah, of course. Yeah, anything notes you can take pics of. Yeah, absolutely, 100%. And you guys can always come back too and watch this over again. Oh yeah, I don't know. I might add some more, but probably with pencil. I need to get an idea across to y'all. All right. So what is this area under the curve called? Go ahead. If I'm circling it with my pencil, what is that area under the curve called, y'all? It's pacemaker potential, which determines the pace of your heart. That's what that word would imply. True story? So what I want you guys to think about is, how am I going to speed up this person's heart rate? Well, to speed up somebody's heart rate, what we need is these action potentials closer together. Yes, no, maybe so? If the action potentials are occurring closer together, then the time between action potentials is decreased. So the more action potentials in a given unit of time, the faster the heart is beating. We'll come back to epi, Heather. You're not wrong, but we need to think about it one step at a time. So we need to get these action potentials closer together. So what needs to happen to this pacemaker potential? Does it need to be longer before hitting threshold, or does it need to be shorter before hitting threshold? So if I shorten the pacemaker potential, what's going to happen to the patient's heart rate? Increase, decrease, no change. If I make it so that instead of hitting out here, I hit right here, well, then I'm going to create another action potential right here, aren't I? Wherever we hit threshold. So what just happened? The pacemaker potential just got shorter. There's another way to look at this, and this tends to be the actual wording that I use in the long run. It's called rate of depolarization. So the pacemaker potential determines the rate tells us speed, of depolarization. The pacemaker potential determines the rate of depolarization. The shorter the pacemaker potential, the faster the rate of depolarization. Does that make sense? If we depolarize faster, we have a short pacemaker potential. True story? And so determines the rate of depolarization. So the next way to think about is if I have a fast rate of depolarization, so the faster the rate of depolarization, increase heart rate. Why? Are we hitting threshold faster or are we hitting threshold slower? Do we reach threshold faster or do we reach threshold slower? The answer is threshold is reached or met, you know, whatever term you guys want to use. Threshold is reached faster. So that's how that all works. If I want to increase a patient's heart rate, do I want to increase the rate of depolarization or decrease the rate of depolarization? I'm just going to keep on this. If I want to increase the patient's heart rate, do I want to increase or decrease the rate of depolarization? Cool. Does anybody have any questions about that? Awesome. So let's think about, oh, we'll get there, Heather. You're not wrong with epi up above. So we'll get there. Just one step at a time, pretty please, because this is a really complex subject. So the next thing to think about here is if I want to reach thresholds faster, if I want to make the rate of depolarization faster, what ions are going to be involved in that function? What do I want to move across this membrane faster so I reach threshold faster? Well, now we come back over here. What's determining the pacemaker potential? What's opening first? Lovely, good. What's opening first? The funny channel. So what if I opened it faster and what if I opened it bigger? What's going to happen to the rate that sodium can leak into the cell? Increase, decrease, no change. And then what if I overlapped it with the T-type calcium channel? What's going to happen to the rate in which calcium can enter the cell? Increase, decrease, no change. And so if I speed up the rate that sodium and calcium can move across this membrane, if I speed up the rate that sodium and calcium can move across this membrane, I reach threshold faster. And therefore, I create a faster heart rate. Last but not least, how do we do this medically speaking? Well, we're going to go into a lot of drawings and diagrams of that later, okay, Heather, and everybody else that's curious. But what we need are drugs that make it so that the funny channels open faster. And we need drugs that make it so that those T-type calcium channels open faster. Naturally speaking, in your body, how are we going to increase the heart rate? What form of communication does your body have to speed up your heart rate? Oh. If you're running from Mr. Axeman, does your heart rate go up or down? Increase, decrease, no change. Running from Mr. Axeman. So what nervous system do we have in place to speed up the heart rate? So even though autorhythmic cells are autorhythmic, they can create action potentials on their own. We can manipulate those action potentials using the nervous system. Does that make sense? Get rid of the nervous system, the heart's just going to beat at a flat rate. We throw the nervous system into play. Now we start to regulate that heart rate. How do we do that? We change the speed at which it hits threshold. The sympathetic nervous system is going to do what? It's going to make it so the rate of depolarization is faster. The sympathetic nervous system makes it so we reach threshold faster. Therefore, the sympathetic nervous system is going to do what to funny channels? Open them faster or slower? Therefore, the sympathetic nervous system is going to do what to T-type calcium channels? Make it so they're faster or slower. Lovely. And this is all going to have to do with the G protein regulated adenylate cyclase, cyclic AMP craziness, and you guys are going to learn about that tomorrow. But the primary way your body can increase the rate of depolarization is with the sympathetic nervous system, norepinephrine and epinephrine. Same thing, AV node has that parasympathetic tone, and we start to remove it when we put epi and norepi into the system. Exactly. It's going to allow action potentials to transport through it faster. Well, faster. How do you guys feel about this? Like it's hard, but you break it down step by step, it's doable. Yes, no, maybe so? All right. What if we want to reach threshold slower? Now, of course, the brain's full. It always is, but we're not done today because summer. Summertime. Well, hold on. You're not wrong. PNS is going to be the answer. So we'll get there in just a second. But what if we want to reach threshold slower? We're not to the parasympathetic nervous system yet in my line of questions. Because I'll try to do things in the same order every time. Helps the brain learn it better. So before, what we asked was, what do we want to do to sodium influx if we want to reach threshold faster? So now, what do we want to do to sodium influx if we want to reach threshold slower? Yeah, you're spot on, Heather. Let's start with sodium, though. Do we want to increase the speed it crosses or slow it down? Yeah, decrease. What about the T-type calcium channel and calcium movement? Let's slow that down. Cool. So if we drew that line, it would look like this, right? The rate of depolarization would be slower, and we'd hit threshold way later. But hold up. Hold up. What if we want to slow it down even more? This is trickier for students, so let me just go with it. What if I took us from RMP and then hyperpolarized us first, and then slowed down that rate of depolarization? What just happened to the time it took to reach threshold? We really elongated that time, didn't we? True story? Again, you don't need to have all this memorized yet. We're going to go back into sympathetic and parasympathetic and how these functions work. But the first thing that's going to happen is we actually hyperpolarize, and then we slow down sodium and calcium intake. So what ion is going to be involved in hyperpolarization? Good, and that's where finally these potassium leak channels come into play. There are transient calcium leak channels, these guys right here. And transient type, T-type calcium leak channels are impacted by the parasympathetic nervous system. When the parasympathetic nervous system, acetylcholine acting on muscarinic receptors, when all that craziness happens, it's going to open up T-type potassium leak channels and cause a hyperpolarization. Again, don't stress if it's too much right now, because we will do it again later, okay? But if we hyperpolarize and decrease the rate of depolarization at the same time, we can really slow that heart rate down when needed. All right. Deep breath. Any questions? Almost definitely just need to go and draw this out. Sure, of course. Be my pleasure. Quick review of everything we've done. The function of the heart is to pump blood over time. Specific volume of blood over a period of time. Mils per minute, this is cardiac output. Cardiac output is determined by heart rate and stroke volume. The heart rate is determined by autorhythmic cells that are producing their own action potentials because they're leaky. The amount of blood ejected from the heart is determined by the force being produced as the heart contracts. These contractile myocardial cells receive their electricity from the autorhythmic cells. Every single time an action potential from the autorhythmic cell reaches the myocardial cell, it's going to cause it to contract. When the action potential goes away, it's going to cause that myocardial cell to relax. The primary or natural pacemaker of your heart is the SA node. And as that SA node produces autorhythmic action potentials, that current is going to move through the atria first, AV node, bundle of His, bundle branches, Purkinje fibers. And as it travels, it's going to hit contractile myocardial cells and cause them to contract. Again, as the SA node produces an action potential, it turns it on and it turns it off. So we're looking at flowing current, but remember it's not on all the time. Only when the action potential is on does current flow, and then the SA node turns itself off. An autorhythmic action potential. Imagine that SA node creating an action potential and that action potential traveling through the rest of the heart. What we're looking at is this portion of the curve. So while it's turned on, this current leaves the SA node and now travels through the conduction current. When is it turned off? When we're not at the action potential. Does that make sense? Then it takes time before another action potential is created. Then we turn that light switch back on again. And another burst of current moves through the heart. Yes, no, maybe so? Does that make sense? Every time there's an action potential, that current's moving through the heart. So how are these autorhythmic action potentials created? Chill. Right now our heart is relaxing. Okay, the heart's done relaxing. It wants to contract, but in order for it to contract, an autorhythmic cell needs to create an action potential. So we're resting, and while we're resting, sodium is leaking into that autorhythmic cell through funny channels. We're still resting. We haven't reached threshold yet, and yet calcium is leaking into that the autorhythmic cell through T-type calcium channels. Finally, boom, we hit threshold. At threshold, negative 40 millivolts, the T-type calcium channels are going to close, but a voltage-gated calcium channel is going to open. And calcium comes flooding into these autorhythmic cells, just rushing in. It's a geyser, it's a torrent. Calcium rushes in, that action potential burst is created. It moves through gap junctions from one cell to the next, and it's being conducted through the entire heart. But at that autorhythmic cell, the voltage-gated calcium channel is going to end up closing, and potassium rushes out of that cell through a voltage-gated potassium channel. At that point, no more current is leaving the autorhythmic cells, so it's not going through the conduction system out to those myocardial cells, the contractile ones, and so they get to relax. There's no current. They're relaxing. They're relaxing. Sodium through funny channels, calcium through T-type calcium channels. Boom, another action potential occurs. That current's going to flood through the heart, and it's going to cause that heart to contract. Potassium out. Relax, relax, relax. Yes, this potassium channel here, this light blue one, is a voltage-gated potassium channel. On this, is that what you're asking? Where the SA and AV nodes are working? This is the SA node. That's what we're talking about right now. This is the SA node. Exactly, the hyperpolarization part, when the parasympathetic nervous system comes into play, that's the T-type potassium leak channel. This guy does not work during normal physiology, only during rest and digest, which is, by the way, parasympathetic tone. So we normally hyperpolarize our heart just a little bit because we have a little bit of tone. Did that answer your two questions, Heather? Did I answer your question? Yeah, this is this is SA, not SV. SA node. It's all right. This is SA. The AV doesn't create its own autorhythmic cells, really, doesn't create its own action potentials, really, unless the SA is not functioning. And then it gets to take over the job. But the AV is more of this place where we get the AV nodal delay. It slows everything down. All right. Let's take another break, unless there's more questions. We're going to review this over the next week. So this is not the only time you're going to see this. Each time we see it, I'm going to go faster and faster and faster. So you should study this tonight. Start from scratch. Make sure that you can draw these action potentials from scratch. Oh, you're welcome. And make sure you can write it out as basically a what happens at 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. And what would happen if we changed 1? What would happen if we changed 2? What would happen if we changed 0? What if we made resting membrane potential greater than threshold? Is anybody going over there going, what if we made RMP, is this a fast heart rate? RMP is greater than threshold, y'all. Greater. We create one action potential, and can that heart ever relax after that point? It's contracted, can it relax? This is potassium chloride. This is what severe hyperkalemia will do. It makes and moves the RMP above threshold, and we kill somebody. Literal death. Don't do this. That's no bueno. All right, anyways, lots of cool questions I can ask about this, but we're going to continue to build on our knowledge base over the next 2 weeks. So just one heartbeat since and more. So try it. Start over. I'm not understanding your question. I'm so sorry. So just one heartbeat since and more contractions. Oh yeah. If RMP is over threshold, you're going to basically get that action potential, and it's traveled down to those cardiomyocytes, but I mean, they can't relax. You're not getting rid of that action potential. Well, there's no way to get back down to rest. It's just not possible. As long as it's above threshold, voltage-gated calcium channels are going to be open. You know. Hypersensitive. What do you mean by that? I apologize. I'm not quite understanding that question. No, that wouldn't be hypersensitivity. I see kind of what you're saying in terms of like a receptor thing. Listen, RMP is not typically going to be above threshold. You have to have severe hyperkalemia for that, and that's why it's used as lethal injection. I mean, we're talking extreme hyperkalemia. But if you have a patient with hyperkalemia, resting membrane potential is going to start to go up. I'll teach you guys how that is. We'll do a later lecture, not today, because we still have blood pressure stuff to go through. But RMP is going to be going up. We get closer to threshold. So does it become easier for an action potential to be created or harder for an action potential to be created as RMP raises? Easier. Easier because RMP gets closer to threshold. That's just the physiology behind the action potential. What you're going to find in real patients is that it's never that easy. Sorry. It's never that easy. So a patient with hyperkalemia will often have tachycardia, but not always. Sometimes they'll have bradycardia. It'll just depend on the other symptoms they're having. So I got to teach you guys normal phys. You guys got to deal with patients later. Let's take a break. We won't make this one very long. So 15 after, that'll give us an hour to go through the last part of our lab. Okay? Okay. Please be back at 15 after for the 13 people that are in class today. We're missing a lot. Okay. Next phase of our day is going to play on this idea of the heart and the function of the heart. But we're going to kind of progress ahead in our lecture material just a little bit to be able to understand how the heart and blood pressure are related. So let's go ahead and open up our Blackboard real quick. I'll show you what we have going on over here. So for lecture material, the type, I can talk, I swear. You'll notice you have a lot of information for this unit. It's where I really started making a lot of YouTube videos. So all of this down here, these are YouTube videos. Blood flow through the heart, cardiac output summary. So if you didn't understand everything related to cardiac output today, boom, I have a YouTube video that walks you back through it, okay? Conduction pathway through the heart. Again, YouTube video that can walk you back through that. Autorhythmic action potentials. For anybody that wants to go back through autorhythmic action potentials in a slightly different way, because I never do things the same way twice, you can click on this autorhythmic action potential YouTube video, and you'll see it's pretty similar to what we do in lecture, right? Where I go and I kind of do this chalk talk. But I walk you through it. I actually draw in every single one of those different types of channels. And then by the end, boom, you're going to see all the same stuff, pretty much done in the same format that I do in lecture, where I explain each type of channel, and then funny channel, T-type calcium channel. They're all color-coded, voltage-gated calcium channels. There they are, VG. They're also known as L-type calcium channels. And then we got our voltage-gated potassium channels, and boom, we've drawn them all in. Everybody clear that this is available for you? You have no reason not to be able to go through, yeah, L-type, long-term is what they're called. And we're actually going to use that term L-type when we get to these myocardial action potentials. So yeah, they're the same thing as saying a voltage-gated calcium channel. So myocardial action potentials. Now, what we know is that the autorhythmic action potential is going to be traveling through conduction pathways, and they're going to hit these contractile myocardial cells. Well, then the contractile myocardial cells are going to be producing their own action potentials. This is what that action potential looks like. These are the channels that are involved. So if you want to get a head start on tomorrow's lecture, you can watch this, myocardial action potentials. And excitation, contraction, coupling, and relaxation. We're going to go through that tomorrow as well. EKGs. So you can kind of go through. This is all basically, this is all Unit 2 stuff right here. You can watch it all if you have the time. And you'll be learning material before coming to lecture, and then it makes lecture a little bit easier. Just depends on how much time you have available. Now, in addition, check it out. I got narrated PowerPoints for the actual lectures. So narrated PowerPoint for cardiophysiology 1, 2, and 3. So if you want to hear a narrated PowerPoint that goes over each one of these slides and what's relevant to your exams, that's where you go for that. Okay, sound good? Everybody clear? You have a lot available. You don't have to do it all. If you're overwhelmed with time, figure out what works best for you and your study techniques. You don't have to use everything that's available to you. Okay, lab today. Just wanted to make sure you guys knew what was available. So labs for Unit 2. We got an hour to go through this. But they're going to kind of relate back to blood pressure. And unfortunately, I think this company here made it so that we can no longer do this. So in order to do this practice clinical skills thing, you'd have to actually register and sign in. I don't know if it costs money. but I just clicked this and it tried to make me do this sign in. Let's see. I guess I have to join. Don't have an account? I mean, currently I'm not seeing a whatever, I don't even care. There you go. Brian Hudson. None of the above. We'll go, I am a nursing student, because most of you guys are. So let's see, create. I guess I have to send a verification code. So then you put in your verification code. Let me look that up real quick. This is kind of a relatively important part of your lab today. So let's see if this works. 6, 7, 3, 6, 5, 4. Verify code, create. Create. What's going on here? Create. Why? What a pain. Let's try this again. My apologies. I want to make sure this is done for y'all here. Should have looked into this beforehand, but I didn't think about it until right now. Three, 6, 8, 6, 6, 2. Verify that code. I don't know. Create. Missing required. Of course. Again, nursing student. Create. Whatever. Cool. I mean, it seems like it's working, right? So normal heart sounds, first heart sounds, second heart sounds. We'll be doing that in a bit. So heart. So yeah, I mean, it sounds you could do this for a while, right? Lungs, blood pressure. We're going to be doing a blood pressure stuff, taking blood pressure. So now you can actually go in and do some pressure cases. So yeah, you get all for free. Awesome. That's fantastic. Now let's see if I do this. Okay. I just did register and sign in, but yeah, this should work. This should work for free. She still yelled at me, silly automatic voice. But yeah, you guys can go in there, register, and then you'll be able to take the blood pressure practice, and that will be a part of your lab report. So get it done, and that will be available to you. Now, blood pressure online doc. So this is a lab handout. You guys, you're feel free to start looking at these lab handouts and stuff before coming to lab itself, but I know I didn't have it right in the schedule. But all these lab handouts, again, tell you the objective, exactly what the objectives are. What are we going to be doing? Describe the information obtained from obtaining a pulse rate. Define the term pulse pressure. Name the instruments used when obtaining blood pressure. Describe how blood pressure is actually measured. What is systole? What is diastole? What is pulse? And what is mean arterial pressure? And then you're going to have to calculate all this by the end. So exercise 1, you'll be doing pulse rate. I'm going to ask you guys to find somebody in your house. Hopefully you have somebody in your bubble, or nowadays the bubbles are a lot bigger or kind of non-existent. Find somebody to be measuring their pulse rate on. Do not do your own pulse rate. And I'll explain how and what a pulse rate is in just a second. And then you're going to also measure blood pressure. Now, most of you guys probably don't have a sphygmomanometer. Everybody say that word fast. Sphygmomanometer. It's like mom in the middle, sphig with a mom, sphygmomanometer. But sphygmomanometers and stethoscopes, you know, these are one way to be able to determine blood pressure. But in essence, they are your blood pressure cuffs with the stethoscope. And you're going to be measuring a specific thing. I'm going to cover that in my spiel today before kind of letting you guys watch the blood pressure lab video, which there is a link to right here. And this is, I think this was Bernice Spear that put this together. But she measures her blood pressure, and you need to go and watch and be able to follow her recordings. Is that clear? Oh, you do? Awesome, Brianna. But yeah, you're going to watch her, and this is where you're going to get your values, and then you're going to use these values to answer portions of your lab report. And it's just a nice way to be able to learn the lab a little bit better and be able to, you know, determine which units and which numbers you really need to be following. Once you do that, you're going to be taking these readings and you're going to be measuring, calculating the pulse pressure and the mean arterial blood pressure. I'll teach you guys how to do that today. The second part of this experiment is to use the practice drill. So this is where that practice drill comes into play. And I just showed you guys how to register for it and that it is free. All right. So yeah, that'll open up in a website. It doesn't like this. Whatever. Yeah, so if that practice drill doesn't open for you, then I have that link in Blackboard for you right there. Okay? Everybody following so far what you will need to do? I'm going to teach you guys how to do all this and what it all means in just a second. I'm just showing you the lab and the lab handout. Everything you need is technically in this lab handout. Everything you need in order to answer all of your lab report questions is answered all through here. Okay, and there's, you know, descriptions on how things are done, but I, of course, have my own methods that we will be walking our way through. Just showing you what's available so that everybody can follow. You guys can watch this video back to find it. So the last thing that you guys have to click on is the lab report. This is the fillable document. So just like the hematology lab report, I have an online downloadable Word document that, boom, you fill out as you go. Instructor reading 1, practice drill subject 2, so forth, so on. Calculate pulse pressures, calculate mean arterial blood pressures. So you're going to have all of that information and you could write it all down on this fillable form. Is this what you guys turn in for a grade? Yes or no? Lovely. The answer is no. Is this one per person or is this one per group? Always one per group. Awesome. Everybody please follow along because there's always 1 or 2 people that don't catch this. This is all, labs are always per group, always. So you guys are going to work on this lab report together as a group. The last part of this lab report is tricky because you have not had the lecture material required, and I'm not going to talk about the lecture material required for this today. I'm not going to teach you guys about baroreceptors. But baroreceptors are all about homeostasis. So how you get this information? Boom. Okay, I'll walk you guys through baroreceptor reflexes on YouTube. And I listed them here for you. There's a really long explanation, baroreceptor reflex, and there's a much shorter explanation in baroreceptor reflex simplified. Keep following. This material on baroreceptors is also listed here in the lecture material tab, because you will be learning about baroreceptors. So I think it's Heart Physiology 3. I think this is where there's more information on baroreceptors for a lecture material. Baro, yeah, baro. No, B-A-R-O, baro. Baro, B-A-R-O, stands for pressure. So in Latin, baro, like a barometer, is something that measures pressure. Baroreceptors are receptors in your body that detect changes in pressure. Does that make sense? B-A-R-O, baro, pressure. Okay, cool. So 32 after, you guys should all be aware of what you have available to you, yes or no? Does anybody have any questions on what's available and what's not available? It's all here. You just gotta do a little bit of looking. Can I get a whoop whoop? The last thing, of course, is no questions. Awesome. The last thing, of course, is right here. The lab report for blood pressure. This quiz that I'm about ready to unlock for you, here we go, is going to be due next lab. So when is the next lab, y'all? How fast do you guys need to get this all done? It's due on Wednesday at midnight. Now, how many students in your group need to go online and fill out this lab report? I love it. You guys are good listeners. I really appreciate the heck out of that. So only one person per group needs to do that, and then that person is going to go in here to the assignment, and what are they going to write? What did you guys write that first time? Yep, you say, here's the person who submitted it, and here's the list of the names of the people that helped. Because if they don't help, they don't get credit. Cool? Everybody clear? All right, and that stuff's all available for you now. Awesome. So lab material, and then here's the lab itself. So let's walk our way through some of these terms, because I love asking these questions, because I think students don't always think about this, and I think sometimes they're taught the wrong material often through life, just life experiences. So again, the two things we're going to be determining here are, one, pulse. And that's what this lab is all about, is pulse. And two, blood pressure. Pulse and blood pressure. So what I'm going to ask you guys, what is pulse? What is a pulse? Keep going. Anybody have anything else they want to add? Same things, different things? Blood flow. I like that. I like that idea. Heart rate, heartbeat, spike in pressure. Ooh, we're getting closer now. So I'll stop you, because you guys are kind of revolving right around the truth, which I love. So, or the non-truth, which I also love. So what most students immediately think of with pulse is they think of heart rate. And they say, pulse measures heart rate. That's a misconception of what pulse is. I'm taking my watch off here. So when we measure a patient's pulse, what we're doing is we're coming down to the radial artery. Remember, we got the radius, this bone right here. So the artery that runs right down, if you find this lateral styloid, anybody, that little bump on the side of your wrist right there, if you feel right behind that, there's this tiny little depression, this little just area just deep right here. And you can put your fingers there, and if you're real gentle, you want to push. You don't want to push super hard. You don't want it to be too light. You want to be somewhere in between. You guys might be able to feel your own pulse. Yes, no, maybe so? Now, can we measure somebody's heart rate using their pulse? The answer is yes. But is it a measurement of their of their heart rate? The answer is no. Because what we're actually measuring in there is blood pushing against your blood vessels and then relaxing, and then pushing and then relaxing. So what exactly is going on with this pulse is that if you take this pulse idea and you start to think about an artery. So here's our blood vessel. What we have inside of this blood vessel is blood, and that blood's pushing against the walls of your blood vessels. Yes, no, maybe so? This is the exact definition of blood pressure. Blood pressure is a measurement of the pressure created by blood pushing against the walls. BV stands for, well, actually we won't do that because that actually stands for blood volume. So we're just going to write out the full thing, blood vessels. So blood pressure is a measurement of how much pressure is pushing against the walls of the blood vessels. So that's the first piece of information. The second piece of information is that blood vessels are elastic. It's a bit tricky. Blood vessels are elastic. So what does that mean? What does elastic mean? I'm guessing most of you guys are going to get this wrong, but I always ask anyways. What does elastic mean? Flexible. And that's the most common misconception of the word flexible, stretchy, sorry, of the word elastic. Most people think that elastic means it's stretchy, and most people think that elastic means that it's flexible, and that's not accurate, and that's okay. So elasticity is a very specific definition, and it has to do with its ability to recoil. So an elastic band or a rubber band, is it stretchy? Yep. When you let it go, what's going to happen to it? It recoils and returns to its original position. Snap back. Good song, too. Yes, blood vessels are elastic, which means that they recoil. Now, here's the idea, of course. If things are elastic, are they also stretchy? Yeah. Yeah, this is called compliance. So compliance is the ability to stretch something, but elasticity is the ability for it to recoil. I don't know if you guys throw away your clothes, after 40 years or not, but not literally, but I still have I road crew at Washington State University, so I had my, athletic sweats because, of course, I had your athletic sweats. You were the cool kid. I still have them. Do you think they have any elasticity left? No. Right? These old sweatpants or these old shorts that have the elastic bands that wear out over time, can they still stretch? Are they still compliant? Can they still move around your waist? Sure they can. But do they recoil and stay on your butt? Probably not, the older they get. Does that make sense? So blood vessels, sometimes, unfortunately, with age or diseases, you can still stretch a blood vessel, but it loses its elasticity, so it doesn't recoil as well. Okay, let's move on. Let's move on. Let's move on. Blood vessels are elastic, which means that they can stretch and they will recoil. Clear as mud? Blood vessels are elastic, therefore they can stretch and recoil. What's the function of the heart? You guys are now expert physiologists. But use your words, your physiology words. You're no longer using pump blood. We're pumping blood over time, eject for sure, but we're pumping blood over time. We're ejecting blood over time. What word did you guys just spend a lot of time on back in lecture? What's the function of the heart? Wonderful. Cardiac output. So from here on out, if somebody asks you what the function of the heart is, you can say cardiac output, and you sound extra smart. SMRT, smart. Function of the heart is to pump blood. Blood pressure, every single time the heart beats, what's going to happen to the volume of blood in your blood vessels? Increase, decrease, no change. So the contraction of the heart, we'll come over here, function of heart, because it's important to all of this. Heart is always important, is cardiac output. And cardiac output occurs because the heart contracts and the heart relaxes, and that's going to determine how much blood leaves the heart over time, right? So as the heart contracts, we call this systole. Anybody ever heard that term before? Probably many of you, but maybe you didn't know exactly what it meant. Systole is the physiological term for the contraction of the heart. So ventricular systole is when the ventricles contract. Atrial systole is when the atria contract. Relaxation gets its own word. Relax, go through it when you want to go to it. Zoolander. Now you guys are all hypnotized by me. Now, relaxation, probably not true. This is diastole or diastole. It depends on who you talk to. Diastole. But I was learned that it's diastole, and I always say that. So the contraction of the heart is systole, and the relaxation of the heart is diastole. Everybody following that part? Okay. Now, the function of the heart is cardiac output. So as heart contracts, what's going to happen to your cardiac output? Increase, decrease, no change. Cool. And now as the heart relaxes, as it goes through diastole, what's going to happen to the cardiac output? Increase, decrease, no change. And how is that going to relate to blood pressure? As the heart is contracting, as cardiac output goes up, what's going to happen to blood pressure against the walls of those blood vessels? Increase, decrease, no change. Lovely. So as the heart contracts, more blood enters those blood vessels, blood volume starts to go up, and that's going to push against the walls. And we're going to feel that pulse. As blood pushes against the artery, it causes the artery to expand out, causes those arteries to stretch. And now, when the heart goes through diastole, what's going to happen to the amount of blood in the blood vessels? Increase, decrease, no change. And now those blood vessels are going to recoil. So pulse is actually a measurement of blood pressure. How crazy is that? It's not a measure of heart rate. It's a measure of blood pressure. And this is an important differential. So follow along with me. Do you guys see how pulse is actually a measure of blood pressure, not a measure of heart rate? Can you guys write that down for me? Pulse is a measure of blood pressure. It's not a direct measure of heart rate. Oh, thanks for writing it in chat. Thank you. I meant it in your notes, but thank you, Tariq. Your literalness is refreshing, and I appreciate it. So how can we use this information to help us with heart rate? Well, we know every single time the heart contracts and relaxes, that's one heartbeat. True story? And therefore, every time there's a pulse, it's an indication that the heart just beat. Cool. So we could use our pulse as an indirect measure. So pulse is an indirect measure of heart rate. But let me ask you guys one last question related to this because I think it's important. Just because somebody doesn't have a pulse, does that mean they don't have a heart rate? If somebody has no pulse, do you like throw your hands up in the air and say, "Oh, they're dead"? Why might they not have a pulse? What is another reason for no pulse as you're measuring the radial artery out here? What did we say pulse is a direct measure of? It's a direct measure of blood pressure. It's a direct measure of blood pressure. So what's going to happen in a patient whose blood pressure has plummeted? Are you going to feel a pulse out here in their arm? No. Does that mean they're dead? No. Do your work. The way you can still potentially measure a pulse, even in those patients, is you start getting closer and closer. I'm holding my axial artery right now. You guys wouldn't even know that. And closer, be able to measure something like the carotid or look at the dicrotic notch, which is right above the manubrium of the sternum. Those sorts of things, you can actually get closer to the heart and try to get a better measurement of a pulse as you get closer to the heart. Again, though, just because they don't have a pulse doesn't mean they're dead. So I hate those movies because I'm a little too literal. Like, you guys know the movies I'm talking about, where the cop or whatever, the fireman goes running up to the person and they check their pulse on their arm and they do that forlorn look. They look up at the other cops around and they shake their head. Yep, exactly, Alyssa. It's like that would never happen in real life. They'd be like, well, shit, there's no pulse. Let's figure out what's wrong. Maybe they're bleeding out internally. Right? Maybe they're bleeding out externally. You got bleeding out. They're not going to have a pulse because they are super low blood pressure, but it doesn't mean their heart's dead. All right, cool. Anyways, there's my little take care of your patients. Don't watch Grey's Anatomy and think everything on there is true. Okay. Everybody have a better understanding of pulse. So what you're going to do with friends, family, kids, whatever the case may be, is you're going to try to measure their radial artery. And you want to try to make a time. You could do it for a full 60 seconds if you want, measure every single heartbeat. But are you going to ever have time in the field to measure somebody's heart rate for 60 seconds? Think about this logically. You go into a car crash or you're in the ER and somebody's rushing through the door with a patient. You're not going to stop and measure their pulse for 60 seconds. You're going to measure it for like 10 seconds, 15 seconds. So from there, you're going to be able to calculate their measured heart rate. Can you guys do that for me on your lab reports? Only measure your patients for 10, 15 seconds. It doesn't really matter. Pick one, 20 seconds. And then from there, calculate what their heart rate would be per 60 seconds. Yes, no, maybe so? Thank you. All right. Second part of the lab has to do with blood pressure. This gets a little bit more complex, but uses some of the same ideas. Systole, diastole, blood pressure pushing against the walls of blood vessels. You guys ready to move on this? Yeah. I'm just going to say yes, because I'm guessing you guys are lagging a little bit because it's me. So let's go ahead and use some space down here. So blood pressure. Okay. Goodness gracious. I don't know what's going on here. So blood pressure, there are two major types of blood pressure. The first type of blood pressure is created as the heart is contracting. The second type of blood pressure is created when the heart is relaxing. Oh, so blood pressure can either be a value related to systolic function or a value related to diastolic function. Does that make sense to everybody? Somebody give me a blood pressure, any blood pressure, their own, national average, whatever you know. You ever gotten, hooked up to a cuff? What blood pressure did they spew back out at you? Great, Alyssa. You got national average right there. Now there's units involved in this. Yeah, awesome. The number without units means nothing. Anybody else throw out a number? Anybody else? Somebody's got to have a blood. Are you guys dead? Are you guys all zombies? I hope you're not. Please don't be a zombie. Although I'll teach a zombie. Why not? Who cares? Zombies are people too. Nobody else has a blood pressure out there? Okay, well, blood pressures exist. 130/85, starting to get into higher values, but still pretty darn healthy. Lower values, nobody like, 90. I know mine's low. Perfect, Andrea. So probably over like 90/60 or 90/70 or something like that. Exactly. Still healthy. The range is big. What do these numbers even mean? Awesome, Andrea. Andy, we'll actually go into why a low blood pressure would be perfect for somebody who's a runner. It would make sense. Anyways, okay, blood pressure. So let's write just the national average down, which is 120/80. This is what you hear. 120/80. Doctor says you got 120/80. Nurse says you got 120/80. You should be like, yeah, I do. You know it. Because this is super healthy. You got 90/70. Yeah, I do. I'm good. You guys are going to learn why in just a minute. But what these are actually saying is that the blood pressure in millimeters of mercury, this is pressure in all physiology physics. Pressure is measured in millimeters of mercury over a blood pressure, 80 millimeters of mercury. Let's go back to these ideas up above here. When the heart contracts, what do you think is going to be happening to that patient's blood pressure? Increase, decrease, no change. And when that heart relaxes, what's going to be happening to that patient's blood pressure? Increase, decrease, no change. And the value of the blood pressure at maximum is going to be right when that heart is contracting. That's when there's going to be the most blood in those blood vessels, and blood is being pushed out into those blood pressures, all a combination of which is a value of systole. And the blood pressure related to that will be high, and we call it systolic blood pressure. And that's what we have right here. This is the highest blood pressure that that patient will have, and this is our systolic blood pressure, systolic BP or SBP. Now, when the heart relaxes, the lowest blood pressure found in your blood vessels is this lowest value. So as the heart relaxes, the lowest value would be is called the diastolic BP. So now you guys are more familiar with when you say a patient's BP is 120/80, what does that tell you? Their systolic blood pressure is 120 millimeters of mercury, and their diastolic blood pressure is 80 millimeters of mercury. Does that make sense? I find a lot of EMTs don't even know this. They're just taught to take somebody's blood pressure, but they have no freaking clue what it means. Is everybody on board with this idea right here? Now, this idea of 120/80 is healthy, but so's 90/70. So's 130/95. There's a lot of ranges of healthy. What does it mean to be healthy? Well, it's not about what your blood pressure is. It's about how much pressure is being applied to the blood vessels over time. How much, it is about homeostasis, you got it. How much blood pressure is being pushed against these walls? How much snapback is there? How much blood pressure? How much snapback? This difference in pressure from maximum blood pressure to minimum blood pressure is called our pulse pressure. Pulse pressure is an important value. Pulse pressure. Kind of need this space over here. So we're going to go pulse pressure. And then I'm about ready to giggle like a little kid because it's abbreviated as PP. PP. I said PP. Our pulse pressure is the difference in pulse, which we saw up here is blood pressure as it gets pushed against the walls, and then blood pressure as it removes that pressure. In other words, it's systolic blood pressure minus diastolic blood pressure. The difference in those two is how much pulse, how much change in blood pressure is that blood vessel seeing. Does that make sense? Pulse pressure is systolic blood pressure, maximum value, minus diastolic blood pressure. That would give us a pulse pressure. It's how much of a pulse of blood pressure are those blood vessels seeing through the life cycle of that patient. Is everybody on board with that idea? Right? Because it's going to push and then it's going to wane, right? It's going to push and wane. So we're going to get stretch, recoil, and how much stretch and how much recoil, bigger stretch, bigger recoil. Ooh, now we're starting to put those blood vessels through more strain. Let's go back to contraction and relaxation of the heart real quick. And I mentioned this last week. I can't remember exactly in what context, but I even mentioned a little bit more today. Which of these two do I tend to think is more important for heart function? Contraction or relaxation? Systole or diastole? Yeah. Diastole is actually, Alyssa, I think you were gone for that part, so you might not have remembered me saying that, but without relaxation of the heart can't fill with blood. If the heart never fills with blood, who cares how strong it beats? If there's no blood in there, it could beat stronger than a whale heart, but who cares? No blood can be ejected, and the function of that heart is cardiac output. So if it never fills with blood, there's no cardiac output. Does that make sense to everybody? Diastole is crazy important. And another way to think about this is during one cardiac cycle is one contraction, one relaxation phase. It's called a cardiac cycle. One contraction, one relaxation phase, one cycle of the heartbeat. Systole only occurs for 1/3 of a cardiac cycle, whereas diastole occurs for 2/3 of that cardiac cycle. The heart beats, boom, and relaxes. So we get this contraction, relaxation, contraction, relaxation. So you can see it's contracting faster than it's relaxing because we need the appropriate amount of time to refill our heart. Does that make sense with blood? Is everybody on my choo-choo train? My crazy town choo-choo train? Awesome. So let's take this back to blood pressure and pulse pressure in looking at how much pressure is being applied to a patient's blood vessel over time. If the heart is relaxing more than it's contracting, are we going to see maximum pressure applied to these blood vessels more, or are we going to see minimum pressure to these blood vessels occurring more? Which one will we see more? Ah, you guys are so good. You're following so well. Does that make sense? I only had 4 people write it, but I'm assuming more people were able to follow that. If my heart is relaxing 2/3 of the time, then my blood pressure 2/3 of the time is at 80 millimeters of mercury. And it's only at 120 millimeters of mercury 1/3 of the time, because that is when the heart is contracting. Yes, no, maybe so? Well, we need to think about this in our patients. The calculation for this is called mean arterial blood pressure, because blood pressure is not always high and it's not always low. It's somewhere in between. It's a mean. So we call this mean arterial blood pressure. This is better known as mean arterial pressure, and we abbreviate it as capital M, capital A, capital P. You must know this, you must know this, you must know this. No if and or buts. You have to know about mean arterial blood pressure for the rest of the semester. It's just as important as cardiac output equals heart rate times stroke volume. MAP is crazy important. Your body revolves around blood pressure. There's 2 things your body cares about more than anything else: mean arterial blood pressure and blood pH. If either of these go out of whack, your body will kill you to fix them. If blood pressure gets too low, your body will kill you to bring it back up. If your blood pH gets too high, your body will kill you to get it back to normal. Kind of crazy to think about, huh? It's a really important homeostatic value. And we're going to have to determine how to calculate mean arterial blood pressure based on all the information that I've given you so far. Mean arterial blood pressure can be calculated. The mean arterial blood pressure has to do with diastolic blood pressure, because the heart is hanging out in diastolic pressure more than it is systolic blood pressure. Does that make sense so far based on what I've already reviewed? So we're going to start with diastolic blood pressure. So we're going to say MAP is equal to diastolic blood pressure. All right. I just glitched, but I think you guys are still there. Okay. Diastolic blood pressure. We're going to start there. So we're going to say our blood pressure is 80 millimeters of mercury. All right. Well, it is 2/3 of the time. So in order to find the mean, what's happening in between, what's the normal mean pressure that's being applied to our blood vessels, we still need to take into account that systolic blood pressure is happening for 1/3 of the time. Does that make sense? So what we're going to do is we're going to add back 1/3 of something. We're not going to add back 1/3 of systolic blood pressure, because systolic blood pressure is so large. We're starting at 80, and what we're going to do is we're going to add back 1/3 of the pulse pressure. So diastolic blood pressure plus 1/3 of the PP, that is your formula for mean arterial blood pressure. So let's do a math problem real quick. We're going to go with this average person. Okay, mean arterial blood pressure is going to be equal to diastolic blood pressure, which in this patient would be 80 millimeters of mercury. And we're going to add back 1/3 of the pulse pressure. Well, how do we calculate pulse pressure? We're going to take the systolic blood pressure, which is 120 millimeters of mercury, and we're going to subtract away the diastolic blood pressure, which is 80 millimeters of mercury. So what's 120 minus 80? 40 millimeters of mercury. So we're going to take 80 millimeters of mercury, and we're going to add back 1/3 of 40 millimeters of mercury. So I'm going to skip a step. Normally, I wouldn't recommend you guys skip steps when you guys are doing your math problems. You have to show your work for me on your lab reports and your lab practicals. But this would be 80 millimeters of mercury plus 1/3 of 40. So if I were to write that all out, it'd be 1/3 of 40, but I said I was going to skip a step, didn't I? So I'm going to go ahead and skip that step. 1/3 of 40 is 13.33333333 over and over and over. So it's 80 millimeters of mercury plus 13.333333 millimeters of mercury. Do we need to worry about the 0.33333 at this point? Are you ever going to tell a patient that their blood pressure is 93.33333? They won't know what the hell that means. So what's the final answer for the typical mean arterial blood pressure? It's 93 millimeters of mercury. That is what the national average for mean arterial blood pressure is 93 millimeters of mercury. Yes, no, maybe so? So what if somebody has mean arterial blood pressure of 85? Does that mean they're dying? No, because there's always, no, Melissa, because there's always a range that we can work with. Okay, I know. But there's always a range that we can work with. You're going to start seeing, I'll teach you guys about blood pressure ranges later. Let's not deal with that right now because lab doesn't, you guys don't need to know all of that. But this particular patient, they need their mean arterial blood pressure to revolve around 93 millimeters of mercury. But a different patient might need their mean arterial blood pressure to revolve around a different number. Each one of you has your own homeostatic value for mean arterial blood pressure. Does that make sense? Every person has their own set point. Cool, awesome. So somebody with like, you know, a 90/60 blood pressure, let's do that real quick, right? Over here, we would have 60 millimeters of mercury. True story? Because we're using the diastolic blood pressure, and we're going to add back 1/3 of the pulse pressure. The pulse pressure here is 30, so the pulse pressure is 30. 1/3 of 30 is 10, so this would be 60 plus 10. That patient's mean arterial blood pressure would be 70 millimeters of mercury. That would be their set point. Somebody with a set point of 93, if it reached 70, oh, that's not good. But somebody whose set point is already 70, it's all right. Does everybody feel more comfortable with calculating mean arterial blood pressure if you were given or had to measure somebody's blood pressure and you got 120/80 or whatever the case may be? Could you guys now calculate MAP? Yes or no? Cool. Practice it. Work with your lab partners on that. That is something you will need to do. You will need to do. And you can see that's done here. So you're supposed to calculate the pulse pressure for instructor 1, instructor 2, instructor 3, instructor 4, drill 1, and drill 2. So you're going to be calculating pulse pressure 6 times. And the formula for that was Systolic pressure minus diastolic pressure. Max minus min gives you a pulse. Calculate the mean arterial blood pressure. That's the other formula. If you go online, you might actually find some other formulas for MAP. Like you might find one that uses 2/3 instead of 1/3, but they're going to be subtracting 2/3. So if you do use another formula from online, it's okay. Just make sure you're consistent. All right, you'll have to be able to do MAP for instructor 1 through 4, drill 1 and 2. Exactly, Ashley. Yep, and we're going to be doing a whole bunch of physiology for that. By the way, what did I, just to remind you something I said earlier in today's lecture, is that I will not test you guys on math in lecture. So just to be clear, this formula for MAP and pulse pressure, you will not be tested on this formula in the lecture exam. Is that clear? Only the lab practical lab report will you have to do math. Awesome. For lecture, you guys are going to learn a different formula for mean arterial blood pressure that is going to indicate physiology. So what variables affect mean arterial blood pressure and how does your body go about changing it? We're going to be doing that for lecture. All right, cool. Now, the next portion of your lab report, this will be the last thing that I end up talking to you guys about, is this sphygmomanometer, cuff pressure. What the hell is going on when people actually put that cuff over your arm, they pump up the pressure, they have this stethoscope. What are they listening for? What's going on? That's what we're going to learn about next. Okay, this approach of using a cuff, an inflatable cuff called the Roche cuff, this ability to hear sounds of blood moving through the blood vessels, it's known as the Korsakoff sounds. Korsakoff. I don't know. I don't know. I'm not Russian. I think it's Russian. But we're going to be learning about how these sounds are created. Okay, and it's going to go pretty darn fast. You guys ready? And using this information, you guys can go ahead and tell me whether you're ready or not. Using this information, you'll be able to answer a big chunk of your lab report. You guys ready? All right, let's take a blood vessel here. Making a blood vessel. I got a big blood vessel. Blood is going to flow through this. And as blood flows through this blood vessel, that's just straight. It's not having to change directions. The blood's not changing directions. The blood's just flowing. It's happy. Tra-la-la-la-la. If I were to put a stethoscope, which amplifies sounds, right down here. So this is my stethoscope. If I were to put this stethoscope here and listen for blood sounds, would I hear blood sounds in this patient? Again, the blood's happy. It's just flowing freely. It's not bouncing against anything. It's just going. So what I want to think about is, do I hear sounds? So I'm going to write hear sounds, question mark. And the answer here is no. If I put a stethoscope here and I just got freely flowing fluid, it's not bouncing against anything, nothing crazy is happening, I would never hear a sound unless I had a really high, unless I was able to amplify the sound a crazy amount more than a stethoscope can do. In physics, all physics, no matter what fluid we're referring to and no matter what tube we're passing that fluid through, if fluid flows freely through a straight tube, this is called laminar flow. If anybody's ever taken a physics class, you probably already learned this. If you're going into sonography, you're going to need to know all about laminar flow. So yeah, laminar flow, fluid flowing freely. That's 3 F's. And are you going to hear a sound if you have laminar flow? Yes or no? Now let's put a cuff on this patient. Okay, so I'm going to put a cuff around this patient's arm, and I'm putting the cuff right here. Okay, this is going to wrap itself right around that brachial artery right there. Okay, so it's going to go around the biceps femoris, triceps femoris, and then the brachial artery is right here, and it'll pinch that brachial artery off if you apply pressure. But if I have a cuff around a patient's arm and I don't pump up that jam, pump up the jam. That ages me. Was that like a song from '88 or something like that? Marky Mark Wahlberg, when he used to be the leader of Marky Mark. 90s maybe, yeah, somewhere around there. All right, but if I put a cuff, so this is going to be a cuff, and I don't apply any pressure to it at all, I don't pump up the pressure, then the cuff pressure is going to be low. Does that make sense? So if I'm looking at cuff pressure here, cuff pressure is going to be less than the highest pressure no matter what. So the highest pressure is systolic blood pressure. Okay, the systolic blood pressure is going to be much, much greater than the cuff pressure right now. Cuff pressure is non-existent. In fact, the cuff pressure is so low that the cuff pressure is less than diastolic blood pressure even. So the cuff pressure in this scenario is so low that it's less than diastolic blood pressure, and it's also less than systolic blood pressure, which only makes sense because diastolic blood pressure is lower than systolic blood pressure. So anytime something is lower than diastolic blood pressure, it's going to be way less than systolic blood pressure. In other words, we made it complicated, but what this is saying is you're not applying any pressure to the cuff. Does that make sense? And therefore, blood can flow freely through that arm. So let's do the next one. And the next one is going to be a blood vessel. I kind of already messed it up, but I'll come down here. So this blood vessel now is going to have that cuff that we're going to start to pump up that pressure. And that cuff is going to squeeze down around this brachial artery. And what that's going to end up doing is it's going to pinch that brachial artery off because the pressure of the cuff is going to be greater than the pressure of the blood flowing through this tube. So the pressure of the cuff, squeezy, squeezy, squeezy. And no matter how much pressure of blood is inside, that blood is not going to be able to make it through this tube. Does that make sense? This blood is going to run into a traffic jam. Yes, no, maybe so? The cuff pressure is so great in this scenario that blood reverberates back this way. The cuff pressure, I'll go ahead and draw this in with this purple. We have tightened this cuff way down. And the cuff pressure is now super duper duper great. In fact, it's greater than systolic blood pressure. And as long as cuff pressure is greater than systolic blood pressure, then we pinch this blood vessel off and no blood can make it through. And of course, if cuff pressure is greater than systolic blood pressure, then it's going to be greater than diastolic blood pressure because diastolic blood pressure is lower than systolic blood pressure. If we were to take our stethoscope and we were to measure down here, below where the cuff is at, there's no blood down here at all. And if there's no blood down here at all, am I going to hear sounds? Nah, this is a no sounder yet again. We got no sound when there's no cuff pressure, and we got no sound when we've pumped that cuff all the way up. Everybody on board with this so far? This is just called no flow. No flow. I got no flow. No flow, no sound. The last scenario. So what you guys probably, everybody's had blood pressure done on them before, but I think what you guys know is they pump up that cuff and it's super tight and it actually kind of starts to hurt, right? They make that cuff super duper tight. And then they have a valve and they release the pressure of that valve and they slowly let the air out of that cuff. Is there anybody that doesn't understand what I'm saying? Awesome. So that's what we want to do here is we want to think about what's happening to the blood as we slowly let the air out of that cuff. You guys might start to already understand what's about ready to happen. As we slowly let the air out of that cuff, what's going to end up happening to that cuff pressure is eventually it's going to start to drop lower than the systolic blood pressure. And systolic blood pressure is going to allow for blood to start to move through this gap because the systolic blood pressure is great enough to move blood through. Yes, no, maybe so? So in this scenario, cuff pressure just dropped below your systolic blood pressure. Now it's still greater than, the cuff pressure is still, that's not greater than, it's still greater than diastolic blood pressure because the cuff is still squeezing on those blood vessels ever so slightly. So what ends up happening to this blood as it comes out of this narrowed area, think about all this blood that's been building up through here. And now we got a blockage of blood. It wants to get over to this side. So what's going to happen to the speed or the velocity of the blood as it's moving through this narrowed isthmus? It's like Christmas, but it's with isthmus. Just means neck. What's going to happen to the velocity of the blood? You got tons of blood moving through a small space. Man, it's going to just pick up. It's going to flow super duper fast. Think of a river. You got this big river and it's heading towards a waterfall and you got rapids, right? We're narrowing this area that water can move. Therefore, it becomes extremely turbulent and much, much faster. True story? So that's exactly what happens as it comes shooting out of this narrowed area. We start to twirl and twist, and it creates vortexes of fluid movement. Boom. And we are measuring for sounds. And man, if we got rapids, if we have a waterfall, we going to hear a sound? Hell to the yeah, we are. Okay, this is called turbulent flow. This is turbulence. This happens over the wing of a jet. Sometimes when that turbulence is too great, all the wind pressure, all the air pressure around those wings causes your plane to drop, you know, hundreds of feet straight down or hundreds of feet straight up. Tons of fun. I cheer, everybody else screams. It's weird. You apply no pressure to the cuff, you hear no sound. You apply full pressure to the cuff, you hear no sound. Then you release the valve. When are you going to hear a sound? When systolic blood pressure gets above cuff pressure, you're going to hear a sound. True story? And this is the last little bit of detail for you guys today that I'm going to let you guys go. But that's exactly what we got going on here. When you go to take this Nope, not that one. Nope. Yeah, go there. No, I missed it. When you go in here to take blood pressure practice, talking about practice? Yeah, I'll never get tired of that. Sorry. I'm still signed in here. So when you click on this, it's basically going to end up showing you the cuff. And they blow this cuff up, right? They're pumping it up, and they went up to about 180 millimeters of mercury. What is the normal average blood pressure, y'all? What is the normal systolic blood pressure? The greatest value you'd normally be? Yeah, 120. So you want to make sure that your needle gauge is at least greater than 120. But doesn't it stand to reason that there's going to be some patients whose blood pressure is maybe 160 if they're hypertensive or something like that? They're going to have a large blood pressure. So you're going to want to pump up this blood pressure gauge all the way up to about 180 millimeters of mercury. You never want to go to 300. You really seldomly want to go above 200. 160 to 180 tends to be pretty safe because 160 is greater than 120. And as long as your cuff pressure is greater than systolic pressure, then you can start to release the air. Does that make sense? So you pump this thing up greater than systolic blood pressure. When you release the air, the valve is going to decrease. And I don't know why it stopped here for this. I don't know what's going here, but come on, drop, 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 drop. You guys can't hear right now, but the sound just started up. So there is oscillatory sound. Did you guys see how the needle started to tick? What is going on? Why is it stopping? You're fired. This website's fired. I'm gonna have to find you guys another like YouTube video to make this work. I'm firing you. Whatever. Did you guys notice how that started to tick? How like, and I'll do this again, and even though it's probably gonna pause. So there's the other cool thing about doing these blood pressure gauges that you don't actually even need to hear a sound really. Right when it starts to tick, boom, and I can hear a sound and that tip is ticking, that is when the cuff pressure just dropped below systolic blood pressure. So what was this patient's systolic blood pressure? If I started to hear sounds at 160, what's their systolic blood pressure? Boom, boom. Does that make sense to everybody? The second I hear sounds, write that number down because that's their systolic blood pressure. When are you going to stop hearing sounds? Exactly. So right when you stop hearing sounds, you write that number down because that's their diastolic blood pressure. Again, when you hear sounds, write that number down. That's systolic. And when you stop hearing sounds, write that number down. That's diastolic. Y'all good? I might need to find you guys another website because I'm signed in and it's still having hiccups on me here. Maybe they have. What? Go away. I don't want LuxDX ICM systems. Leave me alone, ads. But we can actually go in and here. Let's see if maybe if we go through here, it works better. Nope, nope. She's still yelling at me. She's mean. This robot voice in my head. She's not my friend. She makes me feel sad. Yep, still stop there. Let me do what I can. I'll figure out what I need because if that practice drill doesn't work, then you guys can skip it. Okay? Is that clear? If that practice drill is not working, you guys can skip it, but don't skip the idea. The idea, of course, is still a powerful one, and you still have on the Word document. Oh, come on. in the lab report. That's where it's at. Nope. Where did I point it out first time? Pulse pressure, activity. Aha, right here. So for part 1 activity, there's a lab video that you guys can get the information from. It's right there, okay? So you're gonna click to follow that link, and that should take you to a YouTube video, I think. See? Yeah, not even a very long YouTube video. And there, yeah, there's Bernice. Oh my gosh, there's a lot of ambient noise. Woo. So this is in the actual lab that's on campus, and they have these huge air vents, and her YouTube video has a lot of ambient noise. So just be ready for your ears to get blown out a little bit. Sorry, guys. Just listen to Bernice, what she has to say, write down the readings that she has to say, and I'll see what I can do about that other website. Are there any questions at all? Otherwise, we are done. We're more than done. We are overdone. We are the most cooked, dried chicken in the world right now. Chicken. Just know I heard you guys. You're doing great following along, answering questions. Super proud of everything that I've seen so far. Keep it up. Keep it up. Push yourselves. And this semester's, I mean, we're already week 3 of 8. So we're already a quarter away done. So get on out of here. Text me if you have any questions. Oh, I will. We'll go swimming like we do every day around this time. Adios, my friends.